Okay, we're going to go ahead and get kicked off. Good morning and welcome back to the second day of our Alternative and Synthetic Fuels for Energy and Transportation Systems virtual workshop sponsored by the University of Alaska Fairbanks, Alaska Center for Energy and Power, which is where I'm from. I'm Mari. I'm a research professor at Alaska Center for Energy and Power, and I'll be your MC today and yesterday. Very quickly, I mentioned this yesterday, but this is the fourth of a series of 4 quarterly workshops in our what we call our Continuing Conversations virtual workshop series, where we're taking a deeper dive into important and timely topics leading up to the Alaska Sustainable Energy Conference this May. On the screen, you see the topics from the first 3 workshops. All the materials you can available online, and the workshops have been recorded. And the workshops from this, or the materials from this workshop, will be up within a couple of weeks. They say 30 days at the most, in case you've missed anything. And we'll also share the presentations of any speakers who agree to make their slides public. If you missed any of these, they're available online. And the 5th annual Alaska Sustainable Energy Conference will be held in person at the Dena'ina Civic and Convention Center in Anchorage on May 19th through the 21st, and hope to see you there. Apparently, we missed early bird registration, which ended yesterday, but there's still plenty of opportunities to register. Okay, so today is our second day, and the agenda today is you'll sit through me listening, hopefully not too long, and then our first session is on alternative fuel engines. And this session will be moderated by Clay Copeland from Cordova Electric Cooperative, and speakers include Kai Portin from Wärtsilä and Josh Mook from Hyliion. The next session it will be on the Alaska Next Gen Syn Fuel Refinery for SAF production, and this will be presented by Deputy Commissioner Catherine Keith from the Alaska Department of Transportation. The next session is a hydrogen and a hydrogen blending case study. This is presented by Laurent Nassif, who is an adjunct faculty with ACEP, and this looks at hydrogen blending in Hawaii and asks the question of whether it could work here in Alaska. The next session will be on a combined heat and power, hydrogen-fueled combined heat and power development and demonstration, and this will be presented by Jazz Singh from Caterpillar. And then we have a session on maritime application, marine shipping, and this will be presented by Kelly Scott from Tote Maritime, and he will be discussing the conversion of their fleet to LNG. And then finally, we have a panel on alternative fuels for transportation. This will be moderated by Michelle Wilbur, who is a researcher at ACEP as well, and the panelists include Xiaowen Chen from the University of Minnesota, Bob McCormick from the National Lab of the Rockies, and Tim Leach from Alaska Clean Cities and Communities Coalition. So with that, I think we can go ahead and, oh wait, I have housekeeping things. Okay, housekeeping items. Introduce yourself in the chat if you haven't already. Share your name and organization that you're with. Oh yeah, and then the overview of how this works is the presenters will be in where there's multiple presenters in a panel. Each presenter will present first, and then there'll be a combined Q&A for individual sessions. The Q&A will be after the presentation. To ask your questions, just type them in the chat. We're not using the Q&A. We're not using Slido.com. We're using chat for messages or for questions, and we'll be trying to curate those questions as time goes on. So go ahead and post them in whenever you have a question. You don't have to wait till the end to put them in there. If you have any technical difficulties, just chat a message to event support, and somebody will help you very quickly. They're awesome. They have helped me tons. And then recordings, as we said already, will be made available on the ASEC Alaska Sustainable Energy Conference website, which I believe Sarah Caroline will post in the chat. So with that, I think we're ready to kick off. We had a great day yesterday. I am really excited about, the speakers that we had yesterday. I'm really happy with the how it went yesterday. I'm really excited about the speakers today. I myself have been learning quite a lot. So let's go ahead and get kicked off with our first panel. Take it away, Clay. Oh, actually, I lied. I can't get it. So Clay Copeland is the CEO of Cordova Electric Cooperative. He is the chairman of the Alaska Energy Authority Board of Directors, and he has over 30 years progression in the Alaska electric utility industries through technical, operational, and senior management roles. Now you can take it away, Clay.
All right, thank you, Mari. Well, we have an exciting panel this morning, a couple of great panelists with some great technologies, and gives me great pleasure to introduce Kai Portin. And Kai has a Master of Science in Electrical Engineering from the Helsinki University of Technology in Finland. He's been working with different development and management positions in research and development at Wärtsilä since 1993. And he is currently working as a general manager of sustainable fuels and decarbonization and heading the new technology development related to gas engines, alternative fuels, and flexible engine operations. So we look forward to your presentation, Kai, and remember, as you have questions, to drop those into the chat. Thank you.
Yes, I will talk to you about what we do with our engines at Wärtsilä when looking at sustainability and future fuels. My presentation here will be, first of all, a little bit about Wärtsilä's role in the journey towards the sustainable future. And then I will go in one by one to these new fuels that we have been using. And I will mostly concentrate on the newest fuel that we have, which is ammonia. But I will a little bit touch on the other ones as biofuels, methanol, ethanol, alcohols, and hydrogen, and a small summary in the end. So bear with me. Wärtsilä was founded already in 1834, and for Alaskan people, we can say we were at that time in the same country, in Russia. And so still we can find the Wärtsilä village on the Russian side of eastern Finland there. We are now about 18,000 people working at Wärtsilä, and we are all over the world. What we do is that we are making 4-stroke medium-speed engines. So these engines, they are used both marine side in as main engines on smaller vessels and auxiliary engines on bigger vessels, and very much on cruise vessels as well. And then power plants that are producing energy in the world, heavy fuel, diesel fuel, and now very much gas as a fuel. So that's where we are. And the size of our engines, we have our naming of the engines are so that 20 means bore 20 centimeters. So it's easy to see that if you have a small or big engine. So from about 1 megawatt per engine up to 20 megawatt per engine on the biggest side. Strategy. Our strategy is very easy today. It's decarbonization, or can you call it sustainability? And we have 3 big targets here now. First of all, we need to get all our engine types to work with sustainable fuels. The second is that in our own operations, we will be carbon neutral. And the third is to help our direct suppliers to be more sustainable. And the goal is to have 25% reduction in their greenhouse gas emissions. So a lot of the work that we now do is for sustainability. And this is important because today 1/3 of the global greenhouse gases come from either energy sector or marine. And we don't want to be a part of the problem, we want to be a part of the solution. And here is what I want to show now, how we do it. A little bit for Alaska. We have, I don't know if you see this picture very well, but in the background, I tried to put in our power plant at Palmer, so north from Anchorage, about the same latitude as I am now in Finland, so very easy plant to set up. Here we have a very big, for us, power plant with 171 megawatt output that runs on either natural gas or diesel. So I hope this could be familiar to some of you. At least perhaps some of you get the energy from their electricity. We are also on the marine side. Here is an example of a vessel, cruise vessel, that will come to Alaskan ports this summer, I think, Star Princess. And it's a quite big cruise vessel, 345 meters long, and can take almost up to 5,000 passengers. And here we also have a lot of engines. So 5 of our biggest engines, and they produce up to 70 megawatt when they are all running full. That they never do, but what a possibility to do. And this is also a green fuel, possible for green fuel, as it can run both on gas, diesel, and heavy fuel now. But in the future, or when, not in the future, but already now, if there is biogas, so liquefied biogas or biodiesel, they can run on that also. So a little bit for Alaska. The transition, what is happening now in the world, we see that we need to go towards more sustainable fuels, green fuels, call it whatever. And today, I would say 98% of the fuel in the world is for the engines. It's diesel or natural gas. But we see that drop-in fuels start to come. We will start to mix in biofuels into diesel and into the natural gas. And development for new fuels like methanol, ammonia, hydrogen is coming. And slowly but surely we are going to a greener world. And our solution for that is to have a multi-fuel engine that is flexible for the fuels that are now and the fuels that are coming in the future. We have always liked to test all the fuels that there is. So here you can see a timeline on the fuels that we have had in our engines. And I have marked green those that I see are green fuels, and then I have a little bit dark green here, natural gas, as biomethane will come into that, or liquefied biogas. So we have never been afraid to try, and some of them are used much now, and some of them are used a little bit less. But we have shown that our engines are suitable for using all of these fuels. The fuel roadmap looks like this. We have 2 mainstream. First of all, it's you are run diesel today. Then in the future you can run biodiesel or HVO, renewable diesel, and then later on synthetic liquid fuel, liquid diesel, made from wind, solar, nuclear, whatever it can be. And then natural gas now as a starting point today as a natural gas, and in the future biomethane or synthetic e-methane. Then we are also looking into or using fuels that are not containing carbon, and that it's mainly ammonia and hydrogen that we are using. And we are looking at it a little bit so that ammonia for marine and hydrogen for energy business, mainly because hydrogen is difficult to store on board in big quantities. So then it's easier to make it to ammonia first and then use it as ammonia. So ammonia is a good hydrogen carrier. And then last but perhaps not least, to use alcohols as fuel. We have started off with methanol, but now also ethanol is an important fuel that we are looking at. As a Finn, I don't know if you know Finns, but in Finland we don't really understand why anybody would use ethanol as fuel when you have so much better use of it elsewhere. But still, our engines can run on it. So that was the general part. I will go now shortly into ammonia and then even shorter into the other fuels. Because ammonia is the newest that we have. So we have not only developed the engine, but also the fuel tank for ammonia and the exhaust after treatment system and afterburner, or if you need to ventilate ammonia out as it's toxic. And here is a picture from our test engine in Norway that we started in 2022. So our journey has been to make an engine, and this was now ready in end of 23. So when we released our first engine, I would say 80% of the work that we have done is to look at the safety. So here you can see all the areas that is important for the safety. And these we have been really pushing. So when ammonia starts to come out now as it's toxic, we will see to that all parts are safe and robust to use. The thing that we are still working very much on is, of course, the training, because there are no ammonia engines out yet, and we will need to train operators, passengers, whatever, to, if needed, service people for operating an ammonia-fueled vessel and to service it. I will not go further into these parts, but if somebody have questions later on, please just ask. And here is then our system. As I said, we have the fuel tank. That is a pressurized or refrigerated, semi-refrigerated fuel tank that then is evaporating ammonia to gas, and then the ammonia is used as gas in our engine. And after the engine, we have after treatment system that removes the NOx and possible ammonia slip that is unburned from the engine, which would be toxic, and where we have rules on how much we can let out ammonia from the exhaust stack. And then when ventilation is needed, or if some other reason that we cannot burn the fuel that has come out of the tank, we have the possibility to have a ammonia release mitigation system, a burner that burns away the toxic ammonia. Of course, this is nothing that we want to do much as it's a good fuel that costs a lot of money. But still, in real life, or you see it now on the picture, it looks like this. We have the engine, the first engine that we have sold will go to Norway. And we have the fuel tank. We have the gas valve unit that is controlling the gas, ammonia gas coming to the engine. And then we have these arms, the ammonia release mitigation system tank. We have now sold two engines so far, so it's a very new one. The first one, it will now be installed. That is the engine you saw the picture also before. It will be installed on a platform support vessel called Viking Energy, going in Norway. We have had gas engines on it since 2003 when it was built, and now they will test or start to use ammonia. So we will throw out two gas engines and put in one new ammonia engine on that vessel. And by the end of this year, the operation should be started. And here we have then the second that we have sold. It's the first new build that we have with ammonia engine, and here we have the full scope for from the tank to and what I have been showing you. So let's see how it starts to go, and I hope that everybody will be interested because this is a nice step forward. This was all about ammonia. Shortly then about methanol, ethanol. Methanol we already started in 2015 by converting a vessel going from Sweden to Germany called Stena Germanica. And they have been running now for more than 10 years. And the operation has been good. And after that, it was totally quiet until 2022, 2022, there suddenly the market woke up and wanted to have methanol engines. So then we were quite quick in releasing different engine sizes for methanol operation. With methanol, there is a short step towards ethanol, as they are quite close. So we have mainly been looking at Brazil now for ethanol operation and doing joint work with Brazilian companies. And we have also now sent out one engine for a demonstration power plant in Brazil at a place called Suape. And this will now start these weeks on ethanol as fuel. I have myself been testing ethanol here in Finland on a similar engine now a couple of years ago. So it looks good. It's more for demonstration for the customer. Last and perhaps least, hydrogen. Hydrogen is the future for many. Still, it will take some time before the world is ready for it. But we are seeing that we will not be the bottleneck. The engine will not be the bottleneck in the development. So already 10 years ago, we started to blend in hydrogen into natural gas to see can we little by little add. And if somebody wants to learn Finnish, vety is Finnish for hydrogen. So after that, we said that if somebody wants to blend in hydrogen into natural gas, then it's okay for us up to 25%. And this has now been demonstrated both in Minnesota and now in the Philippines this year. Now we are also developing pure hydrogen engine, and we have made a power plant concept for hydrogen engine, and this can now be released when the customers want to have it. Last picture is this blending of hydrogen. We can see that hydrogen taken on board a vessel is not so easy, so we are doing joint development with a startup company called Hycamite to crack natural gas into hydrogen and maybe then use the hydrogen in fuel cells or then mix it into the engine to lower the greenhouse gas emissions. What we will get out of this Hycamite is, I don't know if you can see it, but I have a pipe here with the carbon. So as a side product, you will get carbon when you take out the hydrogen. And this carbon, according to the company that makes it, it's a very good carbon. So they can sell this then afterwards. So this is a very nice carbon capture, I would say, when you get pure carbon. So summary, I think that the decarbonization is important both in the marine and energy sector. And we can do and we should do a lot. And we need all the people. We need material people. We need sales guys. We need designers. We need producers, everyone to get this to work. At Wärtsilä, we already provide a portfolio that fills in many of the empty rooms, but not all. And we are happy that more are coming in to help us there. The key for us is the fuel flexibility. You have to be good today in order to be good tomorrow. You cannot sit and wait until the world has changed. So you have to do something that works well today to be good tomorrow. So fuel flexibility is the key for us. And then last but not least, we are testing on our engines, demonstrating biofuels, ammonia, hydrogen, methanol, ethanol. And for me as a test engineer, seeing is believing. So when I see that something works, then I understand it. And the second is doing is learning. When you do something, you learn how you can do it better. Thank you. This was all from my side now.
Okay, thank you very much, Kai. And I see we already have a couple of good questions in the chat box there. Others are welcome to submit their questions there, but we'll go ahead and introduce Josh Mook and have his presentation. Then we'll take all the questions together at the end. So, hello, Josh. Good morning.
Morning.
So, Josh is committed to fostering disruption and innovation, and that's the core of his company's mission. He brings a wealth of his passion and expertise to complex system engineering, design, engine development, leadership, and driving transformative change. So Josh has been at GE for 20 years and has successfully led the introduction of numerous groundbreaking technologies, systems and revenue, and converted those into revenue service across numerous power and manufacturing applications. He's a proud graduate of GE's prestigious Edison Engineering Development Program, which provides him with a comprehensive mastery of cutting-edge technologies blended with practical engineering. So, Josh, thank you for presenting this morning, and we look forward to what you have to share with us.
Awesome. Thank you very much for the introduction, and thanks for the invite. So as was mentioned, my name is Josh Mook. I'm the CTO here at Hyliion. And most of you probably don't know Hyliion or the product Carnot. So I'm going to take some time today and hopefully share that with you and what we're doing to rethink power generation as we know it. And so dig right into it. A little bit about the company, since, like I said, we're probably fairly unknown across the board, but Hyliion is a company who has taken a fairly disruptive thermodynamic system, and I'll get into details about that here as we go through today. And what we're trying to do is develop a very highly deployable, highly efficient, very low emissions impact, things like that, system that you can generate and put on site at any location, just like you would. You're going to have potentially air conditioning systems or heat pumps, things like that at a location. We believe that technology has gotten to a point in power gen where you can also generate power on location, and that doesn't just need to be in necessarily remote areas, but also, really for anyone. So a little bit about Hyliion. We're founded in 2015. Our headquarters is in Austin, Texas. That's where we do all of our manufacturing and scale up, assemble systems. And then Cincinnati, Ohio, which is where I'm sitting today, is our research and development hub, where we do a lot of the product development and initial testing, certification, things like that. So what is the Carnot system? So there's a picture of it on your screen. And what this is a four-shaft system that uses what's called a heat engine technology. So what that means is we're going to convert heat directly into usable electricity. And it does so at a 200 kilowatt building block. And so that core that you see there on the screen, there's two shafts that are very obvious, and then behind it there's two more shafts, represents 200 kilowatts of usable electrical output to the end user. And then we simply scale these as needed, meaning in plurality, of course, in order to achieve higher power levels if you need that. I sort of mentioned this, but I'll get into some more detail. But because our only need from a core perspective, the thermodynamics only need heat to operate. What that does is opens the door for us to use just about any type of fuel that you can use to oxidize and create heat, is now a compatible source of fuel for this core without changing any hardware. So let me get into a little more details about what's going on the inside. And so what I have on this view is a cross section through one of those shafts in the bottom right, and sort of simplified it for ease of understanding, but I'll walk you through a little bit how the system works. So in the very, very middle of the system, we have what's called a linear generator, or just generator for short. And this is a permanent magnet generator, so very high efficiency. But the way it works is quite different than you would see in traditional rotary generators, whereas this one actually translates back and forth as depicted on that picture, and is solidly attached to those shafts and pistons coming out of either side. As that shaft moves back and forth, it displaces our working fluid, which is shown in the red and blue volumes. Blue designates that the working fluid has been cooled. Red designates that it's been heated. And through the rapid and repetitive expansion and compression of that working fluid, that's what moves the magnets, and that's what generates the electricity. What's interesting in this is, unlike an internal combustion engine where the inside the piston chamber you would breathe or inject fuel as well as your air or your oxidizer, and that then rapidly explodes or combusts to create pressure moving this. Ours is completely different in that everything that you see, the heater, the chiller, the generator in this image, is completely hermetic, meaning we put the working gas in at the factory, which is we use helium as that working gas. It gets sealed, and then it stays inside for essentially the rest of its life. And all you're doing is on those reactors that are shown on the very outside, you're reacting your fuel and your oxygen using a process we call flameless oxidation, and I'll get into that a little bit later, to generate the heat that then moves into the system. So only the heat moves into the system and creates the movement, which eventually results in electricity. Again, and I'll get into a lot of details on this, but one of the key enablers that this allows is not only very high efficiency, so you can see electrical efficiencies that can be in the 50% net category. It also has a whole usable heat cycle if you do want to recover that heat for things like building heating or other heat source needs like in industrial applications, but does so without the internals of the engine, so to speak, ever communicating to the outside world, which means it has unbelievably high durability as well, because it's sealed up and stays sealed for its entire life. What allows all of this to happen is very complex and high effectiveness heat exchangers. And so if you think about the way this system works, I mentioned we're not injecting fuel, we're not injecting air into the system itself to combust like you see in traditional ICEs, all we're doing is moving that heat. Well, to move heat and only heat across metal barriers is actually quite complicated. And so it requires very complex heat exchangers, which we manufacture using additive manufacturing or metal 3D printing, and may otherwise be known as. And we do this both in our Cincinnati and Austin facility, and we print all three major components of this core using additive manufacturing in a variety of alloys suit for use for their application. But what that gives you is sort of these heat exchange effectivenesses that are, sort of on the high end of what physics allows, and because of that you're able to convert more of that heat into usable electrical output, which is then exportable to your facility or to your load, whatever that may be. So what we do is we take that core, which is the heart of the system, and you can see it in this image there, kind of in the center of the module, as we call it, the power module, and we wrap the entire balance of plant and control system and around it. So this is an image of the final product. It obviously has the side panels removed, so you can see what's going on inside. But in this module here, you can export that 200 kilowatts of usable electricity out, and it's just fuel in. So everything else you need is inside, including all of the control, the fuel metering, the cooling, you name it. Even has a onboard high voltage battery for load levelization, as well as things like black start and things like that. On the output side, so it's fuel in. On the output side, you're going to get 200 kilowatts of electricity out. By native design, we export DC electricity, which has some really, we think, advantageous ways that it can then tie in with things like renewables that you may have on the facility. You may have a battery already for load buffering and things like that, or you could be doing things such as EV charging, or you're starting to see a lot of even data centers go to direct DC. So we have chosen to export 800 volt DC directly, and then if you do need to then use that for an AC load, we have simple inverters that we marry up with that and get unbelievably good efficiency on the AC side as well. So that's a little bit about the product, really easy. I should also mention, I think I'll get into this later, but small footprint. So what it's literally in a parking spot, as you can see here, and takes up only a fraction of it. So it's about 24 square feet from a footprint area standpoint to get that 200 kilowatts of usable output. So a little bit of what makes it different than other systems. So part of the reason, right, we're all here talking today is this fuel flexibility bit. It takes over 20 different fuels in the exact same hardware. So one inlet, 20 different fuels can come in, and you get that same output on the electrical side. I mentioned a lot of the reduced footprint, but what I didn't mention was also the very low emissions. So for things like natural gas, as an example, without any after treatment, without any catalyst whatsoever, we'll receive numbers on the order of 2.5 ppm or less on NOx and 3.5 ppm or less on carbon monoxide, with no methane slip in this case. And what that does is that even meets the most stringent of South Coast of California's emissions requirements, as an example. So it gives us tremendous amount of ability to go dispatch anywhere and meet any permitting standards that would be there. I didn't say this earlier, but because it is hermetically sealed, there's no exhaust per se, as in a traditional internal combustion engine. Everything is very quiet, so it's going to be at conversational levels. 67 dB is what we typically measure for standard operation, and easily you can have a quiet, a conversation over it, even when you're standing right next to it. So very plausible to put outside of any sort of building and use as primary power without disrupting, the environment that of your facility. I talked about superior efficiency. I talked about low maintenance, so I won't necessarily get into those again. What I didn't say is on the maintenance side, there are no oils or lubrication. So again, that system is completely sealed. No combustion product ever gets into the inside where like the pistons or the bearings are, and for that reason, it's a full gas bearing system, meaning no oil to change ever. Just don't worry about it. Leave it shut. It'll work quite nice. Just digging into a little bit, I kind of mentioned the emissions numbers that you see, and you see those repeated here, sort of very low levels of NOx and CO with no detectable VOCs. But what I wanted to show on this one is on the left-hand side, just a glimpse of what's happening on the inside. And so this is actually one of our reactors where we're responsible for oxidizing the fuel. It's been part of the metal exterior has been replaced with a quartz tubing, so you can see on the inside. And what you're actually looking at the very bottom of this image, sort of the red, is that's the main heat exchanger that's glowing, sort of conveying that it's very hot. But what you don't see is any flame or any combustion process. It's a completely flameless process, which means we're able to keep things like radical formation very low, keep the overall peak flame temperatures very low, and ultimately that's what results in these very low emissions numbers, sort of regardless of fuel. I'm going to use natural gas as the standard here because it's the easiest to compare against. But you don't really see a big change fuel to fuel. So what I thought I would do is we have a quick, just minute and a half video to go through. Dan, a gentleman named Dan, is going to walk us through sort of the system in a little more detail and show you what's going on inside. So we'll take a look at that and then we'll wrap it up.
The Carnot Power Module's heat engine configurations separates power generation from heat production, allowing it to operate on up to 20 unique fuels. There are many factors that can impact the cost and availability of a given fuel. In the short term, a specific fuel could be impacted by natural disasters or geopolitical tensions. Long term, shifting environmental regulation, changing technology, or infrastructure investments may make different fuels more desirable. The Carnot Power Module eliminates many of these short and long-term fuel risks by allowing a single power module to run on many different fuels. In an internal combustion engine or gas turbine, air and fuel are compressed, burned, and then expanded inside the device to make power. The Carnot Power Module is a Stirling heat engine, where air and fuel are reacted at ambient pressure to create heat. That heat is then transferred into the electrical generating moving section of the engine, where it is converted to work through the cyclic heating and cooling of a sealed gas. Because the reaction process is not limited by things like piston timing or the amount of air compression, the Carnot can operate on a large variety of liquid and gaseous fuels without modification. We have identified up to 20 different fuels that the Carnot could run on and have successfully demonstrated operation with natural gas, propane, diluted methane fuels that could be collected from a landfill or agricultural operation, hydrogen, diesel, and ethanol. True fuel flexibility means the Carnot can run on the lowest cost fuel today, continue to produce power if that specific fuel is unavailable, and still run on the fuel of the future.
All right. So just to kind of wrap things up here, I talked a lot about the configuration on the left, the 200 kilowatt module, which I described was sort of that 24 square feet. You can see here it's actually 3 feet in width and about 8 feet long with similar height. So very, very manageable in terms of size and deployability. But also, if you want to gang these together for higher power outputs, one of the projects that is we're currently working on for various end-use applications applications is our higher power modules. So these will be made up of essentially 800 kilowatt blocks. And so the example on the right is a 2.4 megawatt version of that. It's the exact same thermodynamics and internals that you're seeing in the 200 kilowatt, but sort of similar to the way you would use multiple batteries for higher power. In a battery application, we use multiple cores to reach those higher powers, and those have been scaled together for, in this case, just about 2.5 megawatts of power capability. So that's something that we're actively working. We'll be ready for testing here later this year as we start to look for final use applications. So last little bit is, which industries are we really focused on? So you can imagine just about everything that uses electricity is a good application. Some areas that we're super focused on at the moment are the 5 that you see here. So defense applications, some may or may not know, but we'll be using these systems on autonomous ships later this year as we are demonstrating those. It's a great use case because of the low maintenance to be used in vessel applications that don't have people on board, as an example, to take care of it. Data centers is a growing demand, as we all know. Our systems have a lot of attractability there, especially because we can natively output DC power, which matches quite nicely with that. And then the last one I'll just highlight for a second is the waste gas. Dan mentioned in the short video there that we can use highly diluted fuels, mixes of fuels. All of those things is completely fine. So in a landfill application, as an example, or maybe a digester where the fuel is infinitely variable and changing all the time, that is really not an issue. Our system can take that, adjust its flow rate depending on the fuel that's being provided, and then can get you your electrical output in the end. So that was my quick overview. So thanks for the time, and look forward to everyone's questions.
Okay, thank you, Josh and Kai, both fantastic, nutrient-dense presentations and technologies. We have a lot of questions, so if we can think lightning round, I'm going to jump back and forth between these questions, and if we can keep answers brief, even yes or no is okay, we might be able to answer all of them. So, Kai, I'll start with you, and from David Lockard, he says, is the dual-fuel Wärtsilä engines operating in Alaska able to operate on crude oil or naphtha?
Short answer, yes. A little bit longer answer. For every crude oil, we need to see what the crude oil is, because it's so much changing, and it's much about viscosity. And then if it's for marine, we need to have, so it fulfills the SOLAS of 60 degrees for flashpoint. So there are these limits, and we have a specification for what crudes we can approve. The same with naphtha. Naphtha goes light naphtha. That's a little bit, but heavy naphtha, yes, that is okay. To keep the viscosity right and have the temperature control, then it's okay.
Okay, great, thank you. And Josh, what's the frequency of the prime mover, the primary moving part in the KARNO power module?
We vary that depending on the load condition, but typically you're going to see, somewhere on the low end as low as maybe 5 hertz, on the high end 20 hertz, so 20 times per second back and forth.
Okay, great. And then back to Kai, is your ammonia engine running on just ammonia or a mix of ammonia plus hydrogen or some other mix?
Yeah, the ammonia engine that we have they are dual fuel engines as such, so they can run on diesel. And when we run on ammonia, we have a small portion of diesel as a igniter. So a couple of percent, so 5% of diesel for just starting the ignition and combustion. You could blend in some hydrogen. We have not seen that it's necessary to do it in our engines, but you could blend in some if you want to. And we have been testing a little bit, but we have not heard that anyone would like to have it yet.
Okay, nice, thank you. And then Josh, back to you. Has the KARNO been tested on syngas, maybe landfill gas? We have a similar question, or coal gas?
Yeah, you bet. So lots of different syngases, as well as other blends of that. Everything from landfills to wellhead gases to digesters, all those work great. As far as coal gas, I don't think that we have run coal gas specifically, but I would encourage the Doug, the asker of that question. Please reach out to me. Let's get our hands on some and give it a go. Love to, always open to doing that.
Okay, great. Thank you. And then Kai, back to Wärtsilä has worked with U.S. regulators to certify your engines. Have you worked with U.S. to certify them for methanol, ammonia, and hydrogen in electricity generation and/or marine vessel applications?
Yeah, if we start with marine vessel applications, every time we start with something, we usually call all the classification societies, for example, ABS in US. When we started the ammonia, I think they were the first ones we contacted because they had some gurus there that knew a lot. And we work with all of them, and we try to get a regulation so that it looks similar with all the classification societies. On the energy side, it's a little bit different, as every state, every nation want to have their own rules and regulations. So we work closely with them, but that is then more state-wise or project-wise. It could be very much differences between them. But that is something we really have to do, and we are doing it all the time. And we have a lot of power plants in the US and now building at the moment.
Nice, thank you. And Josh, I might lump two questions here. One kind of refers to the raw gases and how much they have to be treated, whether it's landfill gas and so forth. And then also there's a question about a projected cost for that 200 kilowatt module.
You bet. So raw gases generally do not need to be treated in any way, at least for the operation of the power system. One thing you have to keep in mind, you may have local regulations that regulate things that are inert to the reaction process, so like siloxanes and things like that. If you're regulated on those are going to pass right through. They'll just be warmer on the output than they were on the input. So that may come into play, but as far as the power system itself, it's not a problem for the power system. In terms of cost, we're still pretty early days, so we find ourselves parked right in between that of I'll say traditional diesel internal combustion and things like a fuel cell now. So we're in the middle. We do continue to anticipate that to drop, obviously, as we gain volume and additional scale.
Okay, great. Thank you. And Kai, I'm going to add a little flavor to this next question in that the U.S. imports tremendous amount of anhydrous ammonia from Australia, have thousands of miles of pipelines. We have certain classes of vessels on the seas, like floating seafood processing ships that handle ammonia anyway for their freezing and so forth. And so do you see that ammonia or methanol will dominate the seas, or at least a part of them?
I think, like I showed in my picture, everything takes time, but we will come to that in sometimes. And Wärtsilä doesn't bet on any fuel. I can do it because I think that now it is the biofuels that are coming first, and then later on, ammonia would not be for marine a bad solution. Because it's rather easy to make hydrogen to ammonia and scalable. And when people start to believe that it's safe, which I do, then I think it has a good future. Methanol, the biomethanol that is there and will be used, I'm a little bit afraid of that there are other users that are willing to pay more for the green methanol and than the vessels. So perhaps a little bit less there, but now it's a lot of it has been a big boom there on methanol, at least here in Europe, starting from Denmark, the Netherlands.
Nice. Josh, back to you. What's your projected design life or your design life for the Carnot generator?
Yeah, so we because we don't have really many maintenance items at all, we're designed for 100,000 plus hours of operation of design life. Now, some of that will obviously depend on your particular use cases, but very high life as you would expect for an asset of this class.
Okay, great. Thank you. Sorry, getting back to my queue here on the questions. Kai, in back to methanol, do you have any engines that might be suitable for marketing, or do you have any that have been marketed or sold on the North Slope of Alaska at this time?
I'm sorry, I don't know exactly now how big engine size it's wanted there, but our smallest engine now on the methanol side is a 3 megawatt engine, and soon perhaps 2 megawatt, and yeah, could be down also on the really smallest. But if the size is okay, then why not? It's there. But from 3 megawatt upwards, it's okay already today.
Okay, great. Thank you. Good question. And Josh, what's the reciprocating mass in the linear generator? And again, you touched on this a little in your presentation, but issues with lubrication or wear speaks back to design life. And how many hours have you actually demonstrated in testing for durability?
You bet. So, I didn't mention this, but this is sort of alluding to also the high transient capability of the system. So the system is able to respond to transients very, very quickly, sub a second. And the reason we can do that is because that reciprocating mass is very light. We're talking 20 kilograms or less. So there's no mechanical inertia in that at all. Essentially a software update and you have a new power output. But as a result, also being light and it's suspended on these gas bearings, as I described, they don't touch at all. There's no the friction. It's just windage, aerodynamic heating. There's no touch. So there is no design life for those. As long as they're continuing to operate as they're supposed to, that will continue to float for the entirety of its life. Our longest system in operation, like I said, we're a startup, so we're still pretty early days, has been just over about a year and a half sort of in operation, but we're continuing to show that more and more every day.
Fantastic. Great application for our microgrids. If you don't have that rotational inertia, it better be responsive.
Yep.
So, Kai, okay. And Kai, we promise we're not going to tell anybody if you answer this question for us, but have you secretly been working with MEA to change their natural gas fuel to renewable fuel? And also, what's the footprint of your system on a ship that you have in service today?
The first thing we don't do secretly, we are promoting that sustainable fuels will be used, and we are showing that it's good to use, but we are not deciding on that, so that was easy. Then the footprint of the engine, like our 25 engine that I showed on ammonia, that is roughly a 6-cylinder is 5 meter long and weighs about 25 ton. And then if you have a genset, it's a little bit bigger, 8 meter long and 40 tons. So that's the engine. And then the fuel system, you saw the fuel tank, roughly the same size. So 1-to-1, and all the small things in between are a little bit smaller. I don't know if you got the picture there, but an engine, 5 meter, all other components are roughly the same, and according to the picture I showed, and are a little bit bigger or smaller.
Beautiful. Well, we're at the bottom. We're at the bottom of the hour, so I want to thank you both for your presentations, and we know where to find you. I have a dozen questions for both of you, and with that, we'll turn it back over to our host.
Thank you.
Thank you.
All right, that was fantastic. Clay, you did a great job firing off all the many questions we got. Next up, we have the Deputy Commissioner, Catherine Keith, Department of Transportation and Public Facilities here in Alaska. She is going to present on the Alaska Next Gen Synfuel Refinery for SAF production. And I'm super excited to hear about this. I didn't know about it at all. So take it away, Catherine.
Okay, wonderful. Yes, hello everybody. It's good to be here and exciting to talk about a project that we've been working on for roughly the past year and a half. And while we're pulling that up, the Department of Transportation, for those of you that are perhaps not in state, we cover our surface transportation, roads, our bridges. We work on our ports and harbors. We also have the Alaska Marine Highway System that we maintain and operate. Our two international airports at Anchorage International and Fairbanks International Airport. We also have public facilities, over 8,000 public facilities, and 5,000 pieces of equipment. So as a big state, of course, there's a lot of ground to cover. And through our transportation program, we often have performance expectations from our federal funders, whether that's pavement condition, bridge condition. Several years ago, as part of the carbon reduction strategy that came out through federal highways, those funds came into the state for purposes of reducing greenhouse gas emissions. That program is actually still an active program, and we work with our federal partners on eligible projects, but that has included electrification of our along our alternative fuel corridors, which we're very excited that with our partners at AEA, we now do have that corridor established from Anchorage up to Fairbanks. And then along with that, we have identified other strategies that would work for reducing carbon. And of course, in the aviation sector, that's one of the hardest to tackle, how we can collectively reduce our aviation emissions. The reason we're talking about carbon reduction in aviation sector is because we're in discussions with other agencies to develop a synthetic aviation fuel refinery here in Alaska at Port McKenzie. We've been working on a technical and economic feasibility study to share amongst national labs, state agencies, interested developers, and investors to evaluate the viability of such a project. So with synthetic aviation fuel, or SAF, there's been a lot of conversations so far in this forum on alternative fuels, and including biofuels, renewable diesel, and likely SAF has come up. We're using the term synthetic instead of sustainable, but we are talking about the same thing. But here, because of our role as DOT with Ted Stevens Anchorage International Airport, the air carriers had come to us about a year and a half ago, indicating their strong need, their interest in being able to have SAF available to them at the Ted Stevens Airport, which is a hub for global cargo. We're the fourth largest cargo airport in the world. So there's a lot of synergy there with global air carriers at Ted Stevens. So when we're talking about SAF, synthetic fuel, this is a molecularly equivalent to Jet A. And what changes, of course, is the source feedstock. So here we're using there's a variety of feedstocks that can be used, of course, anywhere from woody biomass, municipal solid waste, or other lipid feedstocks. And the method of conversions that are approved are from Fischer-Tropsch, hydroprocessed esters and fatty acids, HEFA being the most common globally currently, as well as alcohol to jet, ATJ. So if we go to the next slide. The scope of our study to date has included this technical feasibility, which is first looking at the available biomass in state. We're looking at the infrastructure that's available, what can be repurposed, what the logistical constraints are for shipping feedstock in and out of a location, what the energy demand is of such a facility to determine if it's even possible to power up such a facility. And from there, we've looked at the cost, the economic analysis of this, understanding what the baseline cost is for SAF, what the market's ability to pay for the gallon of SPK as SAF, and from there being able to come up with a cost per gallon of the SAF that would be put then upon the consumer, whether that's a cargo airline or a passenger airline, that cost per pound or that increased cost per ticket. So those things come together have given us a comprehensive picture for what we're looking at, which is what we wanted to talk through today in this presentation, and then also offer some next steps, because this presentation is not available publicly yet, but we're working to have, we want to have work sessions with those that are interested to help dig deep into the different aspects of this study and understand if there's any errors and assumptions, and being able to update this before we have a published final copy of this. This is a state-led initiative. The governor, Dunleavy, governor of Alaska, had expressed the support for a synthetic aviation fuel refinery to support our air carriers. And we've been driving this as a state project since then. I will say, Department of Transportation doing the chemical engineering on a biofuel, a synthetic fuel refinery, certainly doesn't always align with our broader mission. So we're looking forward to having additional partners in place to help us move this project to the next level. Go to the next slide, please. So as I mentioned, there's demand here in state. Often that's the first problem, who's going to buy it, depending on the cost, of course, to produce it. But here, because at Ted Stevens, we're fueling over 900 million gallons a year, that it doesn't include what the Air Force bases and military bases have. So because of that, we've reached out to the air carriers, FedEx, UPS, Delta, to ascertain their level of interest, and they've provided us back letters of interest with the approximate amount of SAF that they feel they could incorporate onto their planes and as part of their system. So because the production of SAF is so significantly low below the demand, we assumed it was there, but of course the details matter, because here we are in Alaska, a very isolated location. We weren't entirely sure how that would play into their larger fueling strategy. But when we've gotten these letters back from the 8 air carriers, it accrues up to 150 million gallons a year of SPK that they would be interested in purchasing. And when I say SPK, I just want to speak a little bit to the differences here for terminology purposes. When we're at the Synfuel refinery, we're producing the fuel. There'll be a number of products that get produced. SPK, as well as naphtha and renewable diesel. That SPK is the Jet A equivalent. So once we blend it, though, with fossil Jet A, that's what becomes the SAF or SAF blend. So when we're producing the 150 million gallons a year, that's of SPK, which we then would blend into our existing fuel supply. Go to the next slide, please. So first, the first major question we came across was, do we have the resources? What is the biomass inventory in state for these available feedstocks, such as woody biomass, hay, fish? We cast a pretty broad net to see what would fit the technologies. So we looked at the amount of beetle kill that we had across the state, largely in the Matanuska-Susitna area, as well as the Kenai Peninsula Borough areas. But of course, there's other available woody areas statewide that material could be shipped in a number of locations. Of course, seafood, we know that Alaska has 60% of the nation's commercial fisheries, so we produce a tremendous amount of fish, the fish oil of which could be used as part of the HEFA pathway. And then because we already are have the infrastructure in place for natural gas and our pipeline, we wanted to see what infrastructure might be available that just currently isn't being used, was decommissioned, or that could have multi-purposes. So these were the resources that we had in state to put forward into a project with. Go to the next slide. So within Anchorage area, just because we are so close from 90% of the industrialized world, our airport, it's pretty fascinating. We have a lot of potential for growth at this location, and we are seeing a growth in our demand in our cargo numbers. So here, because of the global requirements that are being mandated, like in the European Union, where they're mandating that air carriers do have an increasing percentage of SAF as part of their fleet fuel composition, the price that they begin to need to pay for that, for not having SAF, is considerably expensive. So being able to get it even in Alaska, they can account that towards other global mandates. You can go to the next one. And here, because of the different resources that we have across the state, we have a lot of mechanisms in which we could make a refinery like this work. Let's go to the next one. So part of our efforts here, we'll learn more specifically about Port McKenzie, but the broader area has a tremendous amount of development potential that's occurring right now as part of our overall vision as a state, where the governor's been leading us to. And you can see in the middle here, we have Anchorage. Right across on that peninsula is the Port of Alaska, and across the Knik Arm is Port McKenzie. We've been working on a design for a tunnel going from Anchorage across to Port McKenzie, where there used to be a bridge concept. We're now going through the geotechnical analysis and some cost work on the bridge. But then there at Port McKenzie, there's actually a rail bed that's not completed, but it has all the embankment constructed to go 30 miles north to connect in to the statewide rail. And there is a developer on board that's completing the engineering and design on that rail bed extension, which would then bring rail all the way to Port McKenzie. That area in general at the port is largely undeveloped. There's agricultural land, but that's remaining area is owned by the Matanuska-Susitna Borough. If you go a little bit further north of those agricultural areas, where you see a spur line going out to the west, that's the proposed West Susitna Access Road, and that builds road access west of the Susitna River, opening up a broad area of land towards recreation as well as resource development. So that land going west, we have the rail, north-south, and the proposed Alaska LNG line, you can see that's in orange. That's the current route for where the proposed LNG line would go, is just west of that Susitna River. So the access network that you see being built up right now pulls together a lot of resources and interconnectivity, which is critical when we're talking about a large-scale refinery, which would be there at the Port McKenzie area. So you can go to the next one. So within SAF itself, of course, everyone's aware we're not producing enough. In 2024, the U.S. had 93 million gallons. In 2025, we had 200 million. I think this year we're projecting about 350. So we're certainly in an upward trend, depending on the success of new facilities coming online. And go to the next one. Okay, so our project specifically, we took the 150 million gallons a year that the air carriers are indicating they would want to buy from us. And we kept that as a constant. So if we want to meet the air carrier demand, that 150 million gallons, what would we need to build around that? What would the size of the facility need to be if that was a constant? And then other things had to scale up or down based on that 150 million gallons. So as we went through the analysis, we looked at a broader array of HEFA, Fischer-Tropsch, alcohol to jet. And ultimately, because of the flexibility and the available resource that we have with our woody biomass, we go more in depth on the Fischer-Tropsch pathway so that we can have a bit more flexibility as we move forward, and it is at the scale that to get us to the 150 million gallons. But right now, I do want to be clear, we're still very open, as this is very preliminary in the analysis, but that's to help us understand viability of a project. We did more in depth on one specific pathway. But at a broad look at this, we would ultimately, because of the hydrofracking ratios, once we get our liquid, the liquid fuel, it would be a split between the SPK, our renewable diesel, and naphtha, and the ratios of which would mean we'd need a total of 230 million gallons of syn fuel to get to that 150 million gallons of SPK. So to get to that 230 million gallons of syn fuel, we calculate that we'll need 4.9 million dry woody tons of biomass every year to be able to produce that if all we were using was the woody biomass. And as a secondary byproduct, that renewable diesel for us is a huge value. Not only will this be used for the Alaska Marine Highway System, but then available for other marine vessels or trucking industry or others as needed. So we're very excited about that renewable diesel piece as well. The Marine Highway System also does fall under some global mandates to reduce their carbon emissions by a small percentage every year. So this renewable diesel will be a huge help for that. And next slide. So within the existing facilities that we looked at, some of them are refineries themselves. Petrostar, which is in Valdez, and the North Pole. These are small topping refineries, so they have pretty limited hydrotreating capabilities. At the Marathon Refinery, this is a large-scale refinery. If you haven't been down there before, I encourage you to take a look at it. It's an impressive facility. That being said, it is focused already on its current processing, so adding additional infrastructure there for SAF, it certainly could be possible, but there's already a tremendous amount of activity that happens there. But they do have the large tanks, the workforce, they have a marine dock. So it is still a high candidate for retrofit for a syn fuel refinery. That's worth talking about further as we go. It has proximity to natural gas already, which all of this would help bring down the capital cost of any project that we have. But the Port of Alaska, that's currently where Ted Stevens has its fuel blended or brought in and then there's a line that goes to Anchorage International Airport from the Port of Alaska. So that's a great location for any blending once we have that SPK brought into the Port of Alaska. And then from there, the air carriers themselves have a fuel consortium. So all of the fuel consortium would come to a consensus on the percentage of fuel. And then at that point, it could be blended at the percentage of SPK in the fuel. And at that point, it would be able to easily be sent over to Ted Stevens, all pre-blended. This would be the ideal way versus one-off fueling for different air carriers. But from there, at Ted Stevens, there's a more limited capacity in our fuel farms there. The electric grid is important in this case, just because understanding what the capabilities are for providing power at different locations will impacts the capital cost significantly if we need to have an independent power plant being constructed. So let's go to the next one. And here's where there's some weird, strange glitch that happens with the title slides. But this is Port McKenzie. This is just a layout map of it. You can see in the red area off to the left where the boundaries are of the borough zoned port land. And right now we have an agreement with the Matanuska-Susitna Borough for a little over 500 acres right there at the port facility, which is just upland from their deep water port here. This is a 60-foot deep draft port. Because of the it's still a developing port, so there's a lot of flexibility right now in how a layout would occur. But because we could be bringing in, biomass at scale and large volumes, the benefit of this site too is that going north and south along that current rail bed that you see as a dotted line, they have the land on either side of that, which is available for laydown yards. So multiple great things about this site. A couple things that will still need to happen if this is a site that we move forward with. One is that natural gas line that I mentioned. The current gas ends about 16 miles from the port itself. So we need to bring in that extra. We have to construct a gas line to bridge that gap. There are plans developed, but that capital cost and that work hasn't started. We also will need to have a power plant constructed out here, depending on the ultimate size of the facility, to be able to have that 150 million gallons of SPK that I mentioned. We would need to have a power plant, roughly 250 megawatts. And therefore, the capacity currently is not there on our grid to bring power out there. So that combined heat power plant is going to be important. We also are going to need to have the ability to sequester the carbon dioxide that comes off of the facility. So from this facility going out into Cook Inlet, approximately 15 miles, we'll need to have another pipeline that brings that gas back out so it can be pumped into one of the basins. So several things that have to happen to make this greenfield site viable. But that being said, the proximity to Port of Alaska and the area to expand is all quite critical. When we talk about getting SAF from the Port McKenzie across, we can barge the fuel. We can also have a subsea pipe that it's about 3 miles across the inlet. If needed, we could do rail or truck, but there's certainly a lot of options for the import and export of fuel out of that location. Go to the next slide, please. So when we look at the woody biomass that's available, We have multiple, and what would be helpful for Fischer-Tropsch facility, we can look at the state's woody biomass, the municipal solid waste, as well as the agricultural hay, which we have farms just north of that Port Mackenzie area. Let's go to the next slide. So it was pretty clear early on when we did the inventory of our fish, available fish oil, that there wasn't going to be sufficient quantity to produce the scale of facility that we were interested in. But that doesn't at all means isn't an ideal option to pursue, just at a different scale. You can see we went through a bit of the conversions here from what we had available from the, say, herring and salmon. And when we consider what's annually harvested in Alaska, so for example, herring, we have 345,000 metric tons. When we consider the oil yield of the average herring and the energy content from that, we ultimately would get 7.3 million gallons of that SPK per year based on the herring if we were able to process all of that bycatch, the byproduct, after a fish is processed, and then convert that and put that into a HEFA refinery. So between herring and salmon, those two, we'd only have 13.2 million gallons a year. So we'd love to continue to pursue this, and perhaps there's an adjacent or additional facility that could be built out at a smaller scale. Fish oil to SAF has not been commercially done at this time to our knowledge. So being able to prove this out would be excellent addition to the other biomass feedstocks available for the HEFA pathway. There's many advantages to the HEFA pathway, one of them being the lower cost of capital and the fact that it's more commercially tested and proven at multiple refineries globally. The Fischer-Tropsch, especially at the scale that we're talking about, is very much less so. So there's more information available at the HEFA pathway and data to compare this against, whereas Fischer-Tropsch is still a burgeoning refinery. The next one, please. It's very sunny out here in Anchorage. So we have we have completed a biomass inventory for fish, for woody biomass, and for some agricultural products, as well as municipal solid waste. So we look forward to making those available soon too on our project website. With fish, you can see the calculated amount of pounds of harvest that occurs, the amount of byproduct, and then the oil that would yield if we assume an average 10% of total weight, oil to weight. And then you can see where that this is, and this is no surprise that we have Western Aleutians as the primary producer statewide. So then we need to, from there, understand how we can get it from that location to, the Nikiski area or up into Port Mackenzie for processing, pre-processing of the fish oil, and do so in a way that doesn't degrade the quality of that fish oil. You can go to the next slide. We did the same thing on biomass, looking at what it would take to get to that 4.9 million metric tons, dry tons per year. That's 4.9 is bone dry tons, and the moisture content, depending on the tree, varies significantly. And so we start coming up with some assumed averages where 15% moisture content is then 5.7 million metric tons. As we start to go through the Fischer-Tropsch process from that dry biomass to where it is gasified, and then from there, there's further energy content loss when we go through Fischer-Tropsch synthesis and it's converted to a liquid. And then once we have a final fuel product, what we're considering is 45 get about 47 gallons of SPK for every ton of bone dry biomass. You can go to the next slide. And this will show you where across the study area we have the standing dead trees. When I mentioned the beetle kill, spruce and birch that we have out there, that equates to about 32.3 million dry tons of lumber. Live trees are about 174.7 million tons. And then from there, we wanted to look at how accessible it was to a road within a quarter mile or 1 mile. So we could start to understand the staging of a harvestry practice. What is immediately available, what may we have to construct some forestry roads in order to access efficiently. And then that helps give us a cost basis for a refinery if this was the only feedstock that we were using. We also have a good breakdown of the type of trees that these values comprise, and we do have, this is by acre, but we also have the moisture content, a percent of ash, and then how close it is to a road based on wood type. There's a GIS site that we can pass along to everybody. We're still finalizing the memos, which are based on individual biomass categories, and then we definitely want to make those available to everybody. The consultant that we had on board with this worked with DNR, AEA, and others to come up with the data that goes into this GIS site.
Hey,
go on to the
Catherine, quick time check. You might want to wrap up. We're a little bit past 10 now. You might want to wrap up in a few minutes.
Holy moly. I'm so sorry.
No worries.
Okay, how about if we just skip to go to probably the next. This one is good. Okay, just a summary of the overall findings of the studies that we have. The cost per gallon of HEFA pathway using fish oil is $6.50, and then the Fischer-Tropsch cost per gallon is $4.30. Ultimately, $4.30 for SPK is tremendous for compared to the cost of Jet A and the cost of what people are purchasing SPK for globally. So this gives us huge encouragement to keep moving forward with this analysis. And if you go down three more slides, we can get to the capital cost, where we have $2.7 million for the cost of the Fischer-Tropsch refinery. And you can see all the different components have been broken out. This was based on a mass and energy calculations from biomass to syn fuel, and then all of the infrastructure requirements and the size of them have been costed out here. And the next slide goes into our OPEX costs, where we also took that mass and energy balance and got calculated how much oxygen we need, how much hydrogen we needed, what the natural gas cost was, and what we needed for the steam methane reforming and the combined heat power plant. And all of that is factored in to get our operating cost per gallon, which again, for Fischer-Tropsch, the CapEx is quite high, but the OPEX is low, making it an overall likely pathway of success for us in Alaska. So I'm so sorry to be running late. I always overestimate how much I can speak to in a short amount of time. And you can please read these slides. If you have any questions, please reach out if you'd like to participate or be involved with the peer review. We are putting the entire study online, where our goal was by today, which we obviously didn't meet, but in upcoming days, you'll see it online, and we can get you those links too. So thank you.
Awesome. Thank you very much. I was going to ask the question of when the report or material was going to be made public. So that's fantastic. One quick question. Somebody asks about the fish feedstock. Is it whole fish or fish scraps?
These are fish scraps, so the byproduct after the processing occurs, whatever value that the processors have for that particular fish product, and then what's left, what they would typically just throw back into the ocean. That's the quantity that we've been looking at.
And then, related, this last one is, have you looked into kelp?
We have not, but given the mariculture developments, we absolutely want to be. So it's not considered yet in this study, but we want to add it. Thank you.
Very cool. Okay, all right. One last one. Has captured CO2 been looked at as a feedstock?
It hasn't been evaluated in the study, but we have had conversations with folks that are developing that technology, and it could certainly, with the Fischer-Tropsch process, it can be a feedstock and go directly into the synthesis, Fischer-Tropsch synthesis. So I think what we're seeing we need is, in addition to the woody biomass, as these other technologies come online, we'll want to be adding them into that portfolio of feedstock, especially as technologies continue to be developed, which give us more options.
Okay, very good. Thank you so much.
Yeah.
All right. Thank you very much, Catherine, for that, for me learning a lot about what is about to happen in my state. Our next presenter is Laurent Nassif, professor with ACEP, and he will be talking about hydrogen blending case study with focusing on Hawaii and asking whether it could work in Alaska. All right, take it away, Laurent.
Okay, awesome. Perfect. Thank you so much. That was a very interesting, actually, presentation. So, but I'll try to see if I can speak a little bit faster, see if I can get us caught up. So today I'm going to talk about hydrogen and hydrogen blading test study, what we've been doing in Hawaii. As I said yesterday, and I will repeat that today, if I can go to the next slide. There we go. I do see things from project management point of view because of my experience in project management. So I really look at operating assets and projects that are in the later phase of development and trying to focus on implementation, what is commercially available, what has been implemented, what is ready to be implemented. So look at things, from that lens as well, right? The financial impact and the operation impact of different assets and projects. So very briefly, what is hydrogen? Hydrogen, we can talk about the element hydrogen, and we talk about that, when we talk about nuclear. But really, in our talks here, we're talking about the dihydrogen molecule. That's what we're focused on. But there are other hydrogen carriers out there. We've seen a lot of them actually already in this virtual workshop. We talked a lot about methanol. We talked about ammonia, and also RNG or methane, which is 1C and 4H. So yes, we're going to focus on H2, but think about conversion or use of any of these other carriers. Hydrogen is abundant. It has a very high energy per mass, but on a volume basis, because it's a gas, it has about half the BTU content of CH4. So what that means is that if you're looking at storing hydrogen, you can use the same, by and large, the same storage media as CH4, but the cost is going to be basically twice for hydrogen. It doesn't have any combustion CO2 greenhouse gas because it doesn't have any carbon in it. So that's one of the major advantage of hydrogen. It's scalable and it has synergies with other carriers like a CH4. So we can blend it with a CH4, and that's something that we're going to look into more detail today. It doesn't have any smell. It doesn't have a visible flame, and it's a small molecule. Why is that important? Well, what that means is that if you're going to put it into your gas line, you need to have an odorant, so you're able to detect leaks. You need to put a flaming agent to be able to see the flame and adjust basically a nozzle to be able to have the same type of flame that you're used to when you use your natural gas. Small molecule is important because that was the reason why there's been a lot of research done on embrittlement and potential leaks of hydrogen in existing natural gas lines. So there was a worry that because it's a small molecule, it can go between the matrix or it can escape through the joints of your gas pipeline. But again, I'll touch more on that later on. The real attraction with hydrogen is that it's ubiquitous, right? You can use it for energy storage, you can use it for transport, firm energy, firm power, and as I mentioned, even nuclear. So it's pretty much usable for any kind of applications that you have. I mentioned that yesterday, and I will do the same today as well. I will be focusing on renewable product. The reason why I'm focusing on renewable product is that by definition, they're not depletable. And also, by and large, they are local. And having a local production is critical for reliability, especially long-term reliability, and also for affordability. So which are the key focus for our talk and for, in my view, for flexible fuels. Okay, so why hydrogen? As we know, fossil fuels are depletable by definition, right? And again, because they're often linked to supply chains that are outside the state, they're subject to both market volatility and supply chain volatilities. Renewable, especially variable renewable like wind, solar, and so on and so forth, need firming. So you can address the daily load and seasonality, which are pretty extreme in the state of Alaska. And the gas and power grids need some capacity and some storage for the management of the loads. And of course, communities need cost-effective, reliable, environmentally sustainable energy that they can rely on. Okay, so we know why hydrogen. So in the hydrogen pathways, today we're going to focus on what is in the blue rectangle. Which is basically the first step of the entire process. And what is in the middle, which is basically the storage aspect of it. I will touch upon conversion of hydrogen blends for power grid, because there's some operating assets that I can point to in the case study, which I think is interesting. Again, we've talked through other presenters have done really amazing presentations on other type of application, ammonia, ethanol fueling station, and then we've seen couple of good examples for power generation as well for these different products. But today, we're going to focus on the first step, which is using any of the resources that we have at our disposal, which are numerous in Alaska, and look at the three pathways for generation of hydrogen, which is electrolysis, gasification, and reforming, and then stop at the production of hydrogen and blending into our infrastructure or storage of the hydrogen. Very briefly about electrolysis, gasification, and reforming. Electrolysis is basically the breaking down of the water molecule into its elements, so H2 and O2, with the action of power. Generally, you want to use curtailed power because it's wasted power. Gasification, in this case, it's a waste to hydrogen process. So basically, with the technology that I'm looking at, it's using any kind of waste, including black bag, MSW, municipal solid waste, and difficult to handle waste to break down the hydrocarbon chains to produce hydrogen. And then reforming, we've seen at length, and the other presenters did a way better job than I did in explaining that. But it's basically, again, breaking down your hydrocarbon chains with the action of steam, water to produce the hydrogen. Okay, a little bit about Hawaii. And this is not a promotional video for you to go vacation in Hawaii. This is just to show, even though it doesn't seem apparent, the relationship and the similarities between the state of Hawaii and the state of Alaska. There is a strong focus on resiliency in Hawaii because we're a chain of islands in the middle of the Pacific. The majority of the population is in one of those islands. It's in Oahu. It's about 1 million or a little bit more than 1 million people, mainly Honolulu. But like Alaska, even though Alaska is part of the North American continent, there's a lot to be said about the fact that those are the two non-contiguous states in the United States, and Alaska also, in a lot of ways, is dependent on import and export, and also is more isolated, from the rest of the mainland. So there's a strong focus on resiliency and reliability. Affordability is also an issue in Hawaii. There's a high cost of living and especially energy, mostly because of the isolation, the need for imports. It's a little bit different in Hawaii. Electricity is a lot more than gas, like by 1 or 2 orders of magnitude. So the gas utility is a lot smaller than the power utility, which is a little bit different. And that's really because we don't have as much of a need for heat than in other places in the US. But we do need gas for tiki torches and cooking and so on and so forth. So that's a little bit different. The market is really in Oahu, the main island. That's where the majority of the population is. The other islands are more sparsely populated. And we actually only have really one power utility and one gas utility. I have to be very careful with what I say. They're like, no, it's not a monopoly. There is one co-op in Kauai, which is doing a tremendous job. And in the non-utility business, there is other gas companies, but really, by and large, there's just one utility for each power and gas. And there is only one refinery left in the state of Hawaii. There used to be 3, then 2, and now there is only the one. Sustainability, we have a mandate for 2045 carbon neutrality. The power utility has a RPS as well. There is a strong focus on sustainability, and we don't have the resources that Alaska has by a large margin. But whatever we have, like geothermal or hydrogen, hydro, wind, biodiesel, we try to develop as much as we can. Okay, so that's for Hawaii. Let me move through the presentation. What you have in front of you are basically operating assets and late stage development projects examples. Okay. What you have in the top corner on the left side, my left side, is the synthetic natural gas plant. This is where the hydrogen in the state of Hawaii is being produced. And actually, I can go in the next slide just to show you a little bit. This is, I know, chemistry shock here, but bottom line, it's using recycled water and the naphtha, which is a byproduct from the refinery, to produce a synthetic natural gas, which is varies between 10 and 15% hydrogen in its blend, depending on the type of naphtha that you get as input. So if it's light naphtha versus mid naphtha versus heavy naphtha. This process has a CO2 capture as well. The CO2 is coming out at a high enough purity that it can be used by food and beverage companies, in this case, for carbonated drinks and so on and so forth. There is other applications for the CO2 if it's a high enough purity, where it can be used for concrete manufacturing. I know in Canada they're using it for metal manufacturing. So there is a monetization aspect there as well. And obviously some of the CO2 and the CO that is being produced is being methanized to increase the amount of methane into the synthetic natural gas via a carbon capture process. This plant uses cutting edge early 1970 technology. So this is a technology that's been there for a long time. That's what I'm trying to say. It's been operating for half a century. Which is generating some issue now because of increasing cost, right? When you have an aging facility, but it's very robust, very solid technology. Definitely a lot of operating assets. On the top right side is a photo of the Sheraton Waikiki. There is a cogen, which is the largest cogen in the state of Hawaii, and it's operating with the same synthetic natural gas blend. So basically, it's been operating for the last decade with a blend of hydrogen and methane without any issues. And this is kind of like some photos of what the facility basically look like. It's a pretty small footprint. The cogeneration is important for the hotel because we don't need the heat as much as you would need, for instance, in Alaska. But we reuse the heat for hot water usage, in the hotel. So that's an application of these ICE, internal combustion engine, with hydrogen blends. And this specific manufacturer, which is Jan Bakker, they used the operating information from that asset to basically create a retrofit for any of the ICE that they have out there to be able to work with higher blends of hydrogen, and all the way up to 100% hydrogen. In the state of Hawaii, actually, 20% of the power is produced by KPLP, which is a large-scale turbine that is agnostic to the type of fuel that you would you would put in to generate the power. And this is very much in line with what Josh was saying and Kai was saying, earlier in the day, with respect to having those cogeneration engines, that can accept, any type of fuels. This is where you're we're heading toward. One more thing on the use of the cogen. In a case of emergency, propane air is the backup. So we've looked at, again, compatibility studies, into running, those engines, commercial and also residential, with propane air, and there hasn't been any kind of issues with respect to that. I will go quickly through two two projects, and then I'll focus more on the transmission and distribution asset of the blending. What is in the middle is basically a photo of electrolysis asset, a small scale electrolysis asset with electrolyzer. In this case, they were using solar. And there is such a project in Hawaii and other places. It's very easy to implement. I think it's better with curtailed power. But that's a project that is not very costly and could be a very nice next step to develop hydrogen and hydrogen solutions. The one in the bottom is modular gasification that was run with black bags, so any kind of waste. And in this case, they stopped at the biogas and they connected that to a cogeneration to produce power. And that's a project that I'm working on, again, in Hawaii and other places, trying to develop those modular technology that are already deployable. Okay. Let's focus on the main asset here, which is the T&D system, which is basically gas pipelines. I know, exciting, right? So it's composed roughly, half of it is steel and half of it is plastic. Not quite that, but pretty close to that. It has one main transmission line, which goes from the west side, southwest side to the southeast side of the island. And it's made of 16-inch, mostly, steel pipes. The rest are basically your service line and your transmission line. It starts at about 500 PSI, ends up around 350 PSI, at the end of the line. Why that is important is because it is very similar to the operating conditions that you have in Alaska. So both in terms of the material and the flow conditions, and that obviously matters. If you're looking at implementing blending into Alaska. Those pipes, the transmission line was established in 1974 when the synthetic natural gas plant was there, right? And has seen basically 10 to 15% hydrogen for the past half a century. Before that, Hawaii used town gas, which was basically 50% hydrogen. And some of those pipes actually have been there for more than 100 years. And I've seen basically 50% hydrogen for 50 years, and then 15% hydrogen for the next 50 years. And some of those pipe sections you can see actually in that slides. Those are actual pipe sections of different diameters. There hasn't been any specific issue with operating a hydrogen blend in Hawaii. So much so that actually, if you ask people in Hawaii, they would not know that they have been using hydrogen in their daily lives. So when I do hear people being concerned, saying, "Oh, you cannot blend hydrogen, you cannot use it, it's going to be having issues," I'm like, I don't think so. I think the experience, is just trumping everything else, right? There is a lot of other data that are available, on the operation of this system. And we've provided that to our partners in the national lab, which have actually put together an entire model where you can, for your specific condition, use those data, to predict, whether there's going to be any kind of issues with blending of hydrogen, and at what point you may experience some concerns. So that's the basis for the application of hydrogen blending into Alaska, and why my experience is that you could do that. Now, a little bit of study is still needed, because the temperature is different in Alaska. I did try to have that implemented into the models that were developed in the national lab. So that's something that I would highly recommend. Basically take that model and then expand it for the Alaska conditions, just to do that final validation before you go to the modeling. This is a photo of an IC and a large-scale engine turbine. And the photo that shows the different flames is basically the color of the flames, depending on the mix of hydrogen that you have. And so the need to basically tune your equipment, which are regular stove that you could find anywhere else, to be able to have the same kind of flame that you would have with a methane blend. Okay, very briefly, this is this hydrogen electrolysis project in Hawaii and in Alaska. Basically, Hawaii has a lot of orange, and Alaska has a lot of green. That's the gist of it. Hawaii doesn't have as much land available. We don't have water in Oahu, though we got a lot in the past months, but that's different. And we don't have the same renewable sources that Alaska has. So that's the bottom line between the two, and that put a lot of pressure on the financials of a project. You don't have those issues in Alaska. The only thing that Alaska doesn't have is the experience with the blending, but you can use the one from Hawaii to get a project, going on. So all the lights are green, really, for implementation of this project in Alaska compared to Hawaii. This is a comparison of the economics using Fairbanks as an example of the 3 different ways of generating hydrogen. Electrolysis. So that's all looking at modular type of projects. And then gasification. Using a module, in that case, it's a 350 ton per day module. And then RNG reforming to produce the hydrogen. As you can see, in Alaska, the economics will look very good for any of these kind of projects. And so it's kind of like a shift in mentality, I think, with respect to hydrogen. Basically moving from very large projects that have a lot of different technical risk associated with them, which in my experience never work, because they're so big that they get delayed, and then the price gets high, and then it's difficult, to continue with the project. So it's a shift from that mentality to basically phased projects. So start by producing the hydrogen, prove that, get that going, and you can get it implemented very quickly. within 2 or 3 years, and then add on to that your methanol or renewable diesel or SAF or ammonia or any kind of additional project that you may want to do. Okay, I only have 1 more minute, but I really wanted to touch upon that point here. What we need to do with respect to a strategy for hydrogen is basically do a phased integration of hydrogen into our blend. The reason why this is the most efficient approach is that by doing so, you can integrate the hydrogen in a staged way and always have a lower cost for the ratepayer compared to the status quo, which is what it is right now. So by doing this phase integration, you're always providing benefits to your ratepayers. Additional benefits to the fact that the hydrogen doesn't have the volatility that natural gas has because it's not indexed. And because it's locally produced, it doesn't have the same volatility due to supply chain fluctuation. It's even more important for Cook Inlet, where we know that the natural gas reserves are decreasing. So this curve with respect to the current natural gas price, will have spikes every time that your natural gas declines. So by introducing hydrogen little by little to compensate some of that decline in a phased way, you can make sure that the ratepayer is always protected from a cost standpoint. So that's the impetus for doing a phase integration of hydrogen and trying and implementing all 3 of those modular generation steps, and then going through a blending approach compared to what they do in the UK, which is basically conversion to 100% hydrogen right away, section by section. Okay, that's all I had for today. I am right on time. I didn't make us gain any time, so I'm sorry about that. But yep, that's what I have.
Thank you very much, Laurent. And I forgot to say, Laurent actually also participated in a panel session yesterday on alternative fuel production. So we're especially grateful to you. Okay, welcome back, everybody. Sorry that you had a little bit of a short break, but wanted to be able to hear what everybody had to say in our earlier presentations. So I now have the pleasure of introducing Jaz Singh, who will be presenting on a combined heat and power, a hydrogen fuel combined heat and power system. Jaz has over 29 years of experience in reciprocating internal engine combustion development and alternative fuel applications. He holds a master's degree in engineering, and in the last over 19 plus years at Caterpillar, he has led various teams for development of medium and heavy duty Tier 4 diesel engines for off-highway machines and industrial applications in the size range of 200 to 800 kilowatt, and for development of large natural gas and dual fuel engines for electric power, marine gas compression, drilling, and well frac applications in the size range of 1 to 4 megawatts. More recently, he's been involved in this CHP development, hydrogen genset development. So I will let you take it away from there, Jaz.
Good morning, all, and good afternoon, depending upon where you are. So this is an overview of our DOE Caterpillar combined heat and power hydrogen system development and demonstration. This was a DOE co-funded program. Yeah, so here is an overview, some high-level planning overview of the project. Caterpillar was the project lead, so we applied for the DOE co-funding against a funding opportunity announcement, and we got an award of $5 million to do this work, and balance of the funding was from Caterpillar. We had several project partners here District Energy St. Paul, or DESP, in St. Paul, Minnesota, National Lab of the Rockies in Colorado. Certarus Limited was our low carbon intensity hydrogen fuel supplier. Ziegler Power Systems is our Caterpillar's local dealer in Minnesota. And McKinstry LLC is the engineering company that we hired for the site development for this during the demonstration. The project goals were to develop a hydrogen natural gas flex fuel CHP genset that is capable of running on 100% natural gas or 100% hydrogen, or a blend of 25% hydrogen and natural gas on volume basis. And then the other part of the goal was integration with and demonstration at a renewably fueled district energy site. So this was a 4-year project. And in first couple of years, we did a lot of R&D work that included 1D and 3D simulations, as well as testing on our single cylinder engine here in Caterpillar. And then in parallel, we started putting together or started converting our production natural gas engine to a fuel flexible engine that can also run on 100% hydrogen as well as the blends. And we also containerized the entire genset along with the combined heat and power, or CHP system, in a container. And the CHP system was to recover the waste heat from the hydrogen or fuel flexible engine. And then we did the development site design, permitting, construction, etc., and installation of the system at that site, and then integration with the District Energy St. Paul power plant. And the last few months were then on the genset commissioning as well as testing or demonstration at the DESP site. There was a big team involved in this 4-year-long project, but first and foremost, thanks to the DOE for giving us the co-funding to do this work, and several project partners that I already mentioned that were included in this, that were part of this project. Some of them got the co-funding from the project, and some were just the vendors. Baker Engineering and Risk Consultants, I didn't mention that earlier, and they were the hydrogen and site safety consultants. There was a big internal team of Caterpillar engineers who helped in this project. And again, this work was done as based on the co-funding received from DOE. This DOE program really, accelerated the development of hydrogen products in Caterpillar. So Caterpillar has for over 10 plus years, we have our gensets that are running on coke oven gas, which can be up to 60% hydrogen. So we did have that experience. But this one was unique in the sense that we were building the capability of running on both 100% hydrogen or 100% natural gas, as well as the blend of those two fuels for mobile power for the stationary power generation. So as a result of this project, we had chance to expedite the development of hydrogen capable flex fuel gensets that can provide 100% hydrogen capability when hydrogen is available, or fallback capability to run partial or fully on natural gas fueling when hydrogen is not available in sufficient quantity or is not available at all. We also have hydrogen conversion kits. So those legacy engines or gensets that are already sold, if those customers want to convert their gensets to accept, either 25% natural gas or 25% hydrogen or 100% hydrogen, they can buy those retrofit kits and convert their natural gas gensets into fuel flexible genset. The new gas gensets from Caterpillar are being sold as 25% hydrogen capable natural gas gensets. We also came to understand, what is the social, financial, and technical barriers. There were a lot of challenges getting all the permits and hydrogen safety, around the hydrogen safety when we did the demonstration. So that was a good lesson learned. And we also gained understanding of, how the power density, efficiency, transient response, and the greenhouse gas emission profile of this hydrogen-based product compares, to the conventionally fueled gensets. So as I said, the initial couple of years were a lot of R&D. As shown here, this is an example of our single-cylinder engine. This is an example of our single-cylinder test engine. So this is just a section of our big 16-cylinder engine, and we do a lot of R&D on a single-cylinder engine to begin with. So that's what we used. Here is an example of CFD simulation that we did to optimize how to inject hydrogen fuel in the intake port of the gas engine. Here are some other pictures from that single-cylinder engine lab, and our gas admission valve that's shown here or here was mounted in the intake port. And this intake port for the single-cylinder work was 3D printed. And this is where the gas admission valve for hydrogen would sit. And air is coming in from this side, and it's going to the cylinder coming out this side with the hydrogen mixed together. So we evaluated, performance with hydrogen, natural gas, and hydrogen plus natural gas blends in this modified single-cylinder engine hardware, and also modified our flame arrestor and identified optimum engine operating parameters or space or boundaries that were then taken into a multi-cylinder engine. All right, trying to move to the next one. So as I said earlier, we took our existing production natural gas 16-cylinder G3516 genset and converted it into fuel flexible genset. So some of the additional changes that we made are listed here: 100% hydrogen port fuel injection system. So we use port fuel injection for injecting hydrogen in individual cylinders. Natural gas is pre-mixed, so it is injected pre-turbo. So it is not injected in every single cylinder, natural gas, but hydrogen is injected in individual cylinders. The pre-mixed fueling system that we had for 100% natural gas before, it was modified to handle up to 25% blend of hydrogen. New turbo finer mesh flame arrestors, cylinder pressure sensing to sense the cylinder pressure in individual cylinders. And then system for crankcase ventilation, because we didn't want hydrogen to accumulate that goes past the cylinders as blow by. We didn't want that to accumulate in the crankcase. Engine controls to handle variation in hydrogen percent in pipeline gas, and other hydrogen compatible components and seals, metals as well as non-metals were also changed. So once this genset was fully put together, then we took it to our large engine test cell at Southwest Research Institute. And then we did the detailed testing on this multi-cylinder engine. So during the natural gas and blended fuel operation, the genset delivered the full 2 megawatt electrical power output. That's what it is supposed to do. And NOx and CO2 emission from that operation was about 1 gram per horsepower hour and 375 grams per horsepower hour. But during the 100% hydrogen operation, the same genset produced, we ran it up to about 1.3 megawatt but because of the abnormal combustion that we saw in one or two cylinders, we limited the power output to about 1 megawatt. So on 100% hydrogen, then that genset would run the max 1 megawatt electrical power output. But this is our first gen of that hydrogen genset. Our second gen is already pretty improved and can run much higher power output than 1 megawatt. One advantage of running 100% hydrogen is that the NOx emission went down to about 10th or less than the 10th. It was about 0.1 gram per horsepower hour compared to 1 gram with natural gas. And there was no CO2 because hydrogen doesn't have any carbon, hydrogen fuel, so there was no CO2. There is a trace amount that comes from the lube oil burning, but other than in the fuel, there is no CO2 going in. But independent of the type of fuel used, natural gas or hydrogen or blend, the genset can ramp up and down between 50% and 100% rated electrical capacity in less than 1 minute. And its overall thermal efficiency is around 85%, up to 85%, electrical plus thermal put together. Overall fuel efficiency is about 85%. So single cylinder work, then the multi-cylinder engine development, and then the whole thing, the whole genset, engine plus generator, along with the combined heat and power CHP system, was containerized in this 40-foot ISO container. And this one, there were some key features that we had to add because of the hydrogen safety, because of the hydrogen fuel. So it was a standard CHP enclosure that we typically use for our natural gas gensets, but with hydrogen integration. And we worked with the CHP packager to put this assembly together. The ventilation system was modified based on the NFPA2, hydrogen leak detection and hydrogen venting and nitrogen purging systems were added. Explosion pressure relief was added. Fire detection and alarms were enhanced because of the hydrogen, and emergency shutoff was also included. Genset room spill containment was also is a standard part of this offering. And then we included or added and tested ECS 200, which is our energy control system. It is a complete controls package that that handles engine controls, genset controls, balance of plant control, as well as the grid connectivity. And then we also used a master microgrid controller on the site to show that it can interface with multiple power generation sources at the site. And then finally, the whole thing was shipped to the site after it was containerized and then integrated on site. Here is salient details of our demonstration site, District Energy St. Paul in St. Paul, Minnesota. They are a non-profit district energy site, and they have a biomass-fired steam turbine combined heat and power system that they have been running for a few years now. They use tree waste from several counties that they bring to their plant, and they post-process it into smaller chunks, those big tree trunks. And then they use that to burn in they produce steam by burning that tree waste. And they can generate up to 25 megawatt of electricity in a steam turbine and 65 megawatt of waste heat that they recover from that system. So green electricity as well as green heat, they have already been producing that for years. And They claim that it helps them avoid about 100,000 tons of CO2 emission each year because they are using the tree waste from their local area. The natural gas-fired boilers are also used from time to time, especially in the winter when this plant cannot meet the requirement of heat from various customers. And they also use electric chillers in the summer. So this electricity that they produce and the waste heat that they recover, they use that to cool the buildings as well as heat the buildings in the downtown St. Paul area, as well as some single-family homes. So they supply them the hot water and cold water from their plant in that district with those houses and buildings in the St. Paul downtown area. And here is a typical temperature, supply temperature, and return temperature of that hot water system. So what we did that we installed our genset and integrated it with their plant. So the electricity from our genset was supplied to the plant, and then the waste heat recovery from our engine was sent to their system, and that hot water was then sent to the city or surrounding district, where it was used to for various applications in various residences as well as in the commercial buildings. This is just going over the demonstration site development. So this is a view of the District Energy St. Paul in the downtown St. Paul area. And our genset was placed on their parking lot here. And then our hydrogen fueling system was placed on this vacant lot next door. And natural gas was taken from the existing natural gas pipeline that was going underground near this site. The McKinstry LLC, the engineering contractor that we hired, they took care of several different permits and approvals, site design permit, building, electrical, mechanical permits, and a conditional use permit, as well as compressed hydrogen tube trailer hazmat permit. So those all were needed to be obtained from the local authorities having jurisdiction. And District Energy St. Paul took care of, helped us with the air permit as well as leasing of this vacant lot. And then Caterpillar, with the help of other team members, took care of the HAZOP analysis, quantitative risk analysis, hydrogen safety plan, pre-startup safety reviews, and site safety and hydrogen safety training, and first responder awareness and engagement. So we went from this initial setup to this fully installed system. And you can see our fuel flexible genset here in the 40-foot container. Up top, you see the radiator and heat exchanger for our combined heat and power system. And then these lines are nothing but the electrical lines going back and forth from the District Energy St. Paul plant, as well as the hot water supply going to their CHP system, and then the colder water return coming back to our CHP system. And then these are compressed hydrogen tube trailers. Because they are at a very high pressure, we used a pressure reduction skid before to supply low pressure hydrogen to our genset through these lines. And here is an example of, I can play that video still, probably not, but this just shows that the 30 seconds video that shows that the genset was ran on site. So we ran the genset in the islanded mode operation because grid paralleling, even though that was our initial intention, but it wasn't possible due to local utility constraints and the timeline of that connection. Initially we ran the genset on natural gas only, 100% natural gas, for about 266 hours. And during that time, we supplied up to 1.9 megawatt of electricity to the power plant. And the NOx output in the tailpipe was 1 gram per horsepower hour. And then we ran, after we were done with the 100% natural gas operation, we switched to 100% hydrogen operation. And we ran it for 206 hours. And up to 1 megawatt electricity was supplied to the plant at that time. And NOx output was less than 10th of what it was with natural gas, and then near zero GHG or CO2 emissions. So we did use a load bank in the initial phase of this commissioning, but as well as during these run hours going up to the full load. But up to 1.3 megawatt electrical load was provided by the DESP plant, and up to 1.9 megawatt thermal engine waste heat recovery was supplied to the DESP plant. Here is an example of when we ran our genset. This is natural gas only operation. So we ran it from 860 kilowatt load all the way up to 1.9 megawatt load. And then this blue portion of the bar is the ISO electrical efficiency. The green portion of the bar is thermal efficiency, and these are the losses. So electrical efficiency 38.4% to 41.5%, and thermal from 46.7 to about 40.3%. So at 55% load, overall efficiency of the package was about 85%, and at 95% load, it was about 82%. And here is a plot for the 100% hydrogen operation. Again, isoelectric efficiency, thermal efficiency, and the losses from the system. And in this case, at 50% load, the package efficiency, overall efficiency was about 78.8%. And with 100% load, it was 79.4%. So various stakeholders, as well as the local folks in St. Paul area, they visited the demonstration site during our press day, as well as our dealers, as well as electrical power customers who were interested in hydrogen also visited the site during the demonstration. That was the last slide. So any questions?
Thank you, Jazz. That was actually super interesting. I have some questions, but let me start with Tim has a question. I know you mentioned, you had reference to discussion on materials for components, seals, et cetera. Can you speak to durability of the materials in general in the genset with respect to hydrogen embrittlement?
Yeah, so we did, based on our single cylinder engine testing, we did look at the combustion components like the piston and liner, cylinder head, etc. But that runtime was about 500 hours, and we didn't really see any changes, any impact of running on hydrogen there. We are looking for opportunities to run this genset for longer hours, like up to 1,000 hours. And then we plan on taking different parts that came in contact with hydrogen for long duration, and then inspect those to see if there is any impact of running on hydrogen. We do not have that data fully yet.
Okay, here's another question. I see that this is a fully containerized system.
Yes.
Can you speak to what the requirements would be, or if it would be even feasible to integrate, a unit, I don't know whether it's, certain percentage or not hydrogen into an existing powerhouse? I don't know if there are
exactly. So during the demonstration, that's what we did. The District Energy St. Paul is a power plant that supplies electricity as well as heat to that district. Actually, they sell the electricity to the local utility, and then they buy back electricity to run their plant. but they sell the heat to the local district. So we integrated this genset into their power plant, as you saw in that picture on the slide, and we ran it over there. So it's fully possible either in a power plant setting or any other commercial setting to integrate this modular, containerized genset.
Okay.
We'll have to take care of the hydrogen safety aspects for any given site, but it is possible to integrate it.
Okay. One last question. We have 1 minute. What other fuels is Caterpillar exploring, or what kind of fuels can your gensets run off of?
Yeah, so like many other speakers have talked about this earlier as well, as I said, we have a lot of experience running our engines on coke oven gas, which has up to about 60% hydrogen. Our engines are also capable of running on biodiesel, renewable diesel, HVO, and as Jim from ORNL showed us yesterday, we are also working on that methanol engine as well, and biogas, landfill gas. Our engines can run on all those fuels.
Great. All right. Well, thank you very much, Jas. That was great, and we will transition to our next speaker. Thanks so much.
Yeah. Thank you.
Okay, our next speaker is Kelly Scott from Tote Marine. Kelly Scott is a marine professional with over 20 years of experience in the maritime industry, including more than a decade sailing commercially in deep sea operations. Kelly has extensive experience working in shipyards around the world and has spent multiple seasons supporting complex and demanding marine operations in Prudhoe Bay, Alaska. Kelly is the project technical lead for the Orca LNG conversion project, which you will be talking about today. And this is the session that stumped me yesterday because I didn't know what Orca was, so I got all confused. And then Gwen saved me and said, "Oh, it's Kelly from Tote." So, all right, Kelly, take it away.
So my name is Kelly Scott. I work for Tote Services, and I was asked to talk about our conversion of our two Orca class ro-ro vessels to LNG. Real quick, the business development guys asked me to give a quick plug for Tote, so here it is. Tote is a collection of companies, brands, if you will. Tote Maritime Alaska is one of them. That's the brand that I support. We also have two ships that operate on the East Coast out of Jacksonville, Florida to San Juan, Puerto Rico. That would be Tote Maritime Puerto Rico. We operate terminals, First Coast Terminals, Puerto Rico terminals. Tote Services, we manage ships. I think we're up to over 33. I think we picked up a couple of ships to manage, as well as new construction. And then we also have an inland shipping fleet, probably recognized names Cargyle, those on the East Coast, if there's any, Aqua Gulf, Manica Government Services, just to name drop a few. So that is my commercial obligation out of the way. Now, what I'd like to talk to you about is Tote's natural gas activities. So in addition to some bunker barges that we've been operating natural gas vessels for a number of years now. On the right of the screen is we call them the Marlins. There are two container ships. They were purpose-built to serve Puerto Rico, delivered in 2015 by NASCO, which is a General Dynamics company in San Diego. That was the build yard. And they were purpose-built to be dual fuel. And they were actually the world's first dual fuel container ships. So that's a feather in our cap. Couple more quick facts. It's a slow speed direct drive engine. So two-stroke. So if you can imagine the engine the size of a three-story house or a three-story building, give you a perspective, it produces 26 megawatts of power. And then they have three auxiliary gensets that are also natural gas as well. So again, purpose-built from, inception of design construction, commissioning, and into service running on natural gas. That's the easy button. Now let's talk about the more interesting one, which is the vessels I operate and work with. Tote Maritime Alaska had two vessels, the Midnight Sun and the North Star, that service the state of Alaska from a weekly service run of Tacoma, Washington to Anchorage, Alaska. Both ships sailing every week. We try to be the fastest way to Alaska, short of chartering an airplane. So our typical voyage time, 66 to 72 hours. And that's covering over 14,000 nautical miles. So we're doing about 24 knots as our max speed. And that requires a substantial amount of power. So the Orcas are diesel electric. So this fits in very nicely with all of the presenters so far, talking about power plants. That's my language. So the main engines, we have 4 main engines on board. Each engine, they're MAN 5864 dual fuel engines, producing 12 megawatts each. So those 4 are able to run on dual fuel, being diesel and gas. We still use diesel during the combustion of gas, as it's our pilot fuel, what we call pilot fuel. So that's takes a lot the place of your pilot light and your furnace. So that's what ignites the fuel charge, because as we know, gas would just compress. It wouldn't set off ignition on its own without the diesel to get that combustion going. We also have 2 auxiliary gensets that are each 3 megawatts. So combined, we can put 52 megawatts onto our ship's electrical board, and then each propulsion motor, because we're a diesel electric vessel, we can have 20 megawatts of power going through each propulsion motor, so to each propeller. So that's combined, we can have 52 megawatts of power on the board. 40 of those can be going to the water propelling the ship, getting it going 24 knots. The reason why that's so important is, one, the Gulf of Alaska in the summer is a very nice place. It's very calm. It's great for a cruise. You can see whales and all kinds of stuff. In the winter, it's a horrible place. We start to get concerned when 8-meter seas, we start to really pay attention to what's going on. 10-meter seas, we start talking about what are we going to do to dodge weather. Hurricane force winds are quite typical in the winter in the Gulf of Alaska. So these ships were purpose-built to handle that kind of conditions, and hence why so much power on board. Preparing for this, I tried to get a little bit of context. So I don't know if this is correct. So anybody, feel free to correct me. But AI told me that Fairbanks uses 14 megawatts of power daily. And so we're producing 52. We're capable of producing 52 on board the Orcas. So as I said, Tote Maritime Alaska decided they had to update these 2 vessels. What was the driver for that is in 2020, the IMO limited the International Maritime Organization, which is a branch of the UN that covers all the oceans of the world. They limited this global sulfur content of marine fuels, went from 3.5 to 5%. So Tote had a couple options. They could either buy ultra-low sulfur fuel, which is what is available at the fuel stations around most of the world now. It's at a very high premium to get the sulfur out of the fuel, out of diesel oil. So that would be a very expensive way to go. The next, probably the cheapest way to go, aside from going back to sales and and rowboats would be something called scrubbers. So there's closed loop scrubbers and open loop scrubbers, and that's taking the sulfur content out of the fuel, or out of the exhaust rather, after it's been consumed in the engine. This, though economically appealing and very technically feasible and proven technology, it didn't really make sense in that you still have a waste stream that you have to deal with. And in the case of scrubbers, how they work is using water to wash the exhaust, and as a result, you get acid. So you're having to either dispose of this acid in a closed loop system. As it accumulates, you dispose of it shoreside and have to deal with that waste stream as a hazardous waste. Or when the technology first came out, they allowed something called open loop scrubbers, which was basically direct injection into the sea. And then at that point, what's the point? So TOTE decided to go for the biggest apple at the top of the tree and go for LNG. LNG inherently does not have sulfur in it, so you don't have to clean up a mess that you don't make. So with that, TOTE started this project in 2013 in the planning, and the planning involved our utility company or our fuel supplier, which in this case is Puget Sound Energy, so the local gas utility company in the Puget Sound area. I'll talk about them more later on in the presentation. MAN, our engine supplier, to give us a engine conversion kit, so we could utilize existing infrastructure, existing assets. Instead of repowering, we could just convert the existing engines. Wärtsilä, I know, although I missed it, I know Wärtsilä was presenting here. What we used is the Wärtsilä LNG pack, and that's the gas tanks, the gas processing equipment, all of that infrastructure. GE is our control system on board the vessel. So MAN and Wärtsilä are technically competitors. So getting the two systems to talk together, we had to route the information through GE, our ship's automation control system. So that was quite a task as well, getting rivals to sit in the same conference, have the lawyers of two rivals allow the engineers to sit in the room together and talk about technical matters, was probably one of the highlights of this whole project. Anybody in systems integration can appreciate that. NASSCO was the original build yard of the vessel. So a lot of the engineering was done by NASSCO. That include piping systems that were modified, and electrical connections, that sort of thing. And then all of this work was executed in Victoria, British Columbia, Seaspan Shipyards, which we are customers of them for decades. We go for all our regulatory dry dock periods. So it was just a natural partner. It's on our trade route, and fantastic product that they deliver. So on screen, you'll see the North Star and the Midnights. The North Star and the Midnights on our sister vessels. On the top left is what they looked prior to the conversion. You can see no tanks. Behind the house, between the stacks, was a very open space. Was just the ramps to lower decks was in that area. So going through the design spiral and different iterations of where we would put all this equipment without losing cargo area, we settled on this concept of these two tanks directly behind the house. One thing that I want to really really drive home here is these vessels were built in 2003. They were delivered in 2003. The planning on them started in 1999. So these are long life assets. We hope to have another 20 years post conversion out of them. So when we're talking, and this is, I'm going to drive this home later, but when I'm talking about this, imagine a long life asset and how to change that long life asset over 40 years to accept new technology and adopt new technology. And some of this technology is extremely different. So going from the original design on the top left to the bottom right, we had to install over 500 tons of new equipment and just new deck structure. So that on a ship, it's a lot different from a shoreside facility where you just, have a bulldozer clear some land and pour a concrete slab. There we have to take in consideration of stability, what it would do for a ship in storm, the impact of cargo movement throughout the ship. Can we still unload it effectively and still maintain our commercial run? If doing this conversion inhibits the business model of delivering freight to Alaska weekly, then the returns on that project start to diminish quite rapidly. So in the bottom right, everything in green is new. And orange piping that you can kind of see, I don't know if I can just kind of see there, is the piping that was installed to the bunker station. The way Toad operates is we are, these two vessels are a roll on, roll off cargo. So think tractor trailers and also autos for auto dealerships or personal vehicles. And then as well, in addition to any project or large cargo, buses, Abrams tanks, Stryker units from the Department of Defense. We've moved it all, mining equipment. So it was really important to maintain that flexibility in cargo, ease of operating the vessel within our constraints of meeting that weekly liner service and not taking away cargo. So a lot of work was spent in the design phase on how to limit the amount of cargo that was lost, cargo stows, because that diminishes the profitability over the entire remaining life of the asset. So that quickly adds up. So, right. So hopefully the video is coming through. As I said, we had to add to existing structure, existing asset. We only had 8-week windows to do this because that was all that the commercial team would allow us to take the vessel out of service, 8-week stints at a time. So a lot of it was prefabrication, a tremendous amount of planning ahead of time. What you're seeing is what we call the A-deck structure coming in behind the house. And this was one of several very large pieces that were brought in. This particular module was built in Singapore and then shipped to Victoria and then installed on the vessel. With that, there's a lot of regulations that are very unique to the marine sector. One that some of the audience might have heard of is Jones Act, so that we are a Jones Act compliant vessel. And one of the constraints that is on us for being a Jones Act vessel is we're only allowed so much steel to be foreign steel. So we had to keep a running table of exactly how much steel by weight was added to the vessel, not only for changing the stability of the vessel of where and how high and what location on the vessel, but also for adhering to this Jones Act requirement. So a lot of planning went into that, and then the outfitting Just to go through some fun facts, everywhere the tanks were installed, that faced the tanks and the gas equipment had to have upgraded structural fire protection. So that was 2,700 square meters of what we call A60 fire protection insulation. And so that's rock wool that can withstand a direct flame for 60 minutes before the opposing side becomes uninhabitable. So 60 minutes of a flamethrower going to it before there's enough heat on the other side that you have to evacuate that space. So a lot of work and a lot of planning in that. LNG pipe work all was had to be ABS qualified. So American Bureau of Shipping is our classification society, and so that ensures quality standards in addition to the typical engineering ASME code for piping. U.S. Coast Guard was very interested in this project right from the get-go. This conversion was the first conversion, certainly the first conversion that was started in North America. And as a result, novel projects attract a lot of attention by regulatory agencies. Coast Guard was in the room during the entire time from inception to commissioning. That's another thing I really need to stress with any conversion project or any novel project really is the dividends that are paid off by bringing the regulators in the room and getting them engaged early and throughout the entire process through education and understanding is so much easier than asking for forgiveness. You develop trust. You get helping hand when you need it, understanding and patience, and it made the project go so much more smoothly by, again, inviting the regulators in the room and working together to also form regulations that are meaningful and common sense. So some more facts, another video. During the conversion, we had approximately 5 kilometers of pipe work. I think that's actually a little light. Definitely know that 53 kilometers of cable pulled is absolutely light. I probably think both those numbers are probably a third of what was actually done for each of those. So on an existing system, imagine your house, existing asset, imagining your house with all the drywall, everything complete. And now having to pull all the drywall and run new electrical cable, new plumbing, new systems in your house. That's what converting to a novel fuel like LNG does for an existing asset like a ship. The plus side, and forgive me, my camera fell when they were landing the tank. The advantage by TOTE going through this process and converting to natural gas was not just for the emissions of low sulfur, but also for the economic benefit of having a fuel source that was one, not as volatile as diesel because it's domestically available at abundance. There is not as large export infrastructure as there is crude oil. So it's a local market rather than a global market. So as we all are experiencing in these present times, events overseas can have amazing impact on any activity that you're doing domestically, though you had no idea it was coming, completely unintentional by yourself, but direct impact to your business and your activities. So by TOTE pivoting to natural gas, it was a way to insulate that and smooth that out. So we could project our fuel costs with a lot more certainty due to its stability. A lot of the challenges that we faced, in addition to just the amazing amount of scope of work, was environmental factors. So because of commercial constraints, we could only take the vessel out of service during winter months. That's when TOTE has a low in cargo to Alaska. Alaska picks up in the summer for project work, for tourism. And so that's when the vessels have the highest demand for freight. So as a result, my group only gets to do work in the winter in February, which Victoria is a nice place to go in February, but during the conversion, in 1 year alone, we got over 25 inches of precipitation in an eight-week period. And trying to weld a ship back together in 25 inches of rain is a bit of a challenge. So again, shout out to Seaspan Victoria for doing a tremendous amount of work in very adverse conditions. Switching to the LNG supply. This is where Puget Sound comes in. I'm ashamed to say I don't have a picture of the plant fully completed. My apologies. But I do have a picture of the tank being erected. So in the background along the waterway is our terminal with all those trailers. So our fuel supply is literally across the street, which is really important for us. Again, having a secure supply chain is imperative to having a consistent service. So our fuel supplier was able to dig a tunnel under the road, under our terminal to the other side. And that's what these gentlemen are watching, a tunnel boring machine coming out in our terminal. And the pipeworks was erected so that we had a refueling pier, and the refueling pier had this loading arm, or a chick stand is the industrial term. So when we come into our terminal, we were able to bring up our ramps and secure our ramps to do cargo operations. At the same time, we've worked it out so that as we come in, the loading arm goes across and we are able to hook up and start our bunkering process. So fuel bunkering, traditionally, when we were on diesel, took 4 to 5 hours. Now that we are on LNG, we are taking fueling is now 6 to 8 hours. A lot of that is due to the administrative paperwork and setting up and pre-bunkering conference that we do every single time to ensure that all our safeties work. Going through testing both the Puget Sound Energy side and the TOTE services side, the ship side, making sure that there is an interface between the two systems. So if one system goes into alarm, the other system reacts accordingly. So it's linking the automation of the two plants. And then once that's confirmed, then cooling down, which is, I believe we're down to an 1.5 hour process of cooling down the pipeline, cooling down to the ship from the bunker station to the storage tanks, and then actual transfer. Once we've transferred, then we have to disconnect That's another photo I looking back, should have put in here, is showing the bunker station after bunkering. It's just a giant ball of ice. So having to warm that up enough to safely disconnect and decouple the chick stand, the refueling arm from the vessel, does take some time. So it's changed our operations for that. We've had to work on our crewing on board and to accommodate that extra burden of testing, bunkering, and making sure that the crew still has rest hours, so that they can still safely operate the vessel as they were before the conversion, but now with all the extra stuff. Couple points about our LNG supply. Our gas is inherently has a lower well-to-wake emissions profile than in other parts of the country. And the reason for that is Canada has higher wellhead emissions requirements, and the gas that is sourced from Canada crosses into the United States at the Sumas border crossing through a pipeline. I believe it's called the Olympic Pipeline, that services the Puget Sound area, Western Washington. It runs pretty much the length of I-5. And then the next connection to the U.S. grid, anything east of the mountains, isn't until you get down to Portland area. But Puget Sound Energy sources, again, from Canada. So technically we're burning Canada gas, if you want to say by the molecule. And again, that's figured into the calculation of our emissions well to wake, lowering that down, because at the wellhead, those rogue methane emissions aren't allowed in Canada, and that cleans up our entire fuel supply chain, even the way up to consumption. So that's kind of important, because the second closing thoughts that I really want to wrap up on is, we started the conversation with why TOTE went to LNG, and that was in response to regulation. We were perfectly fine running on diesel. It's a very easy fuel to deal with. It's very safe. Not a lot of safety concerns as far as flashpoint. Politically, it's a very normal thing. It's being very normalized in society. So by regulation having us move to something that didn't have sulfur, TOTE had to put in a tremendous effort, spend Herculean resources to make this possible. Now, as we're looking at new regulations, the IMO is moving towards decarbonization. Decarbonization goals for the marine sector is net zero by 2050. This is the really important bit. Conversion projects like this are essential if we are going to meet those goals. So it doesn't matter if it's methane, ammonia, methanol, or even battery electric. What's important is that we keep trying to make existing assets as clean as we can, while building new assets that meet the latest requirements. I was at a presentation 2 years ago, and one of the most stunning facts that was thrown out was, if you took every shipyard in the world and you matched it with every ship in the world, as far as the capacity of the shipyard to build at whatever size, and then whatever size those vessels are in the world, to replace all the ships in the world it would take every shipyard in the world 12 years of producing ships, one a week. The world has not seen those production levels for ships since 1945 with the Liberty ships that were supporting the efforts of World War II. Today's ships are far more complicated than the Liberty ships of yesterday. So we also need to look at existing assets in order to meet these huge, lofty goals of getting to net zero. And if that's adopting yet another fuel after LNG, or even better yet, reducing our energy consumption, this is something that we need to focus on existing assets, long life assets, and short life assets, as much as it is just building new assets. It's not something that we're going to build our way out of. So with that, I was trying to keep it nice, short, and sweet. Yeah, so that would be my presentation.
Thank you, Kelly. That was tremendous, impactful. I do not think I'm completely overwhelmed with the logistics that goes around these conversions, but that was amazing. Thank you very much. We don't actually have time for questions, so we're going to move on to our next panel, but I might ask you questions via email.
Yeah, by all means. Thank you.
All right, great. Thanks so much. And so jumping quickly into our last panel of the day, this panel will be moderated by Michelle Wilbur, my colleague here at ACEP. She leads the Grid Edge Research Group. I'm going to let Michelle introduce her panelists. So Michelle, take it away.
Thanks so much, Mari. So I am really more personally concerned in research on the grid side. So my background has been mainly in looking at electric vehicles and how those fit into the Alaska landscape. So I am very excited about this panel so I can expand my understanding in alternative fuels for transportation. First up, we have Jiawen Chen, who is currently an assistant professor at the University of Minnesota. He's previously worked as a senior engineer at the National Renewable Energy Laboratory, and we can call it that because that's what it was called when he worked there. He has more than 20 years of experience in biomass pretreatment, deconstruction, and conversion. So he is notably the inventor of a patented deacetylation and mechanical refining process for converting corn stover to ethanol. I'll let him talk more about that if he wants to, but please welcome Jiawen to talk to us today about alternative fuels.
Oh, thank you, Michelle. I think it's a good morning and probably good afternoon for a lot of people. My name is Jiawen Chen. So I'm as an introduction, I'm currently working at the University of Minnesota. So yes, I worked on biomass conversion to produce fuels, especially ethanol and the sustainable fuel in the last 15, 16 years. I'm still continuing this work with Sapphire Renewables, which is recently acquired by Conestoga. We are trying to build a 10 tons biomass per day pilot facility in Liberal, Kansas. We are going to use those ethanol produced from corn stover to upgrade into sustainable aviation fuel. So today I want to give you a brief introduction to SAF. So let me start with the demand side. So air travel is projected to nearly double by 2050, and aviation fuel already accounts for about a share of transportation energy use that is about 8% of that. So what is really critical here, unlike the ground transportation, for example, bus or rail or cars, aviation fuel cannot be electrified because at least in the near future, right? So because the current state of the energy density of the jet fuel is much higher than for the batteries. So the battery is only about 2.5% compared to the jet fuel of energy per mass compared to the jet fuels. So, and the US consumes about 26 billion gallons of the jet fuel, and they are going to increase every year. So, as I mentioned, the jet fuel is a high energy density liquid fuels, right? So, and it is contains mostly from C9 to C12 of the hydrocarbons. If you look at the compositions, it contains about 20% of the paraffins, 30% of the isoparaffins, and 26% of this cycloparaffins and also those dicycloparaffins as well as aromatics. It not only serves as high energy fuels, but also it serves multiple functions. For example, it is a coolant, right, to help for heat transfer media. It will serve as a lubricant, hydraulic fluid, blast fluid, swelling agent, and all these kind of things to make the aviation plane to work. So it has to meet multiple of the ASTM codes. So, for example, D1655, D7566. So you have to make sure the SAF that we produce that we actually for this aviation purpose has to be drop-in compatible. You can just not simply substitute a fuel without meeting those stringent requirements. So as we know, the SAF it becomes not only a really important component for decarbonization of the aviation sector, but also it is a critical component for energy security. For example, we know what is happening right now in the Middle East, and that actually disrupted the supply chain of the aviation fuel. As I recently, my wife has to travel back to China, and we just noticed the airplane tickets has been increased dramatically. So what we can use to produce SAF, right? So SAF is really a good alternative to make sure we have this diversified domestic supply. So what we can use to make a SAF? Well, one of the biggest source right now is using for SAF is oil seed, right? So for example, soybean oil, camelina oil, camelina seed oil, and you can a lot of the for example, one of the biggest company in United States to produce SAF is World Energy, and they use FOG, the fats, oil, and grease. Now, basically the same, right? But oil seeds contains mostly is triglyceride, and FOG contains mostly free fatty acids. They are processing wise, they are a little bit different, but mainly they are fatty acids to produce fuel to produce SAF. Another source is algae. Well, algae has been discussed for many years. Algae contains up to 70% of the oil, and it does not need to occupy of the terrestrial land. That is the advantage of the algae. But the biggest problem for algae is the cost, right? So the cost for growing algae is very challenging. If you want to produce that in open system, which you don't need to have a covered system, well, that is cheaper, but you often have contamination. But if you want to produce algae in a closed system, that increases the cost significantly. The other source is, for example, terrestrial feedstock like agricultural wastes or forest residues. Corn stover, switchgrass, sorghum, they all can be converted into sugars, and sugar can be converted into ethanol or alcohol. And there's a technology converts alcohol into jet fuel, and it has been approved by ASTM TM standards. Forest residues, as far as I know, there's one trial in the commercial trial. This is done by USDA, and I believe the company is. I forget. Sorry, but I think they actually worked together to produce using the forest residue to produce the first aviation fuel that has been used in an aviation, in flight. That is for agriculture feedstocks. The other thing is municipal solid waste and industry carbon monoxide, the mixed waste gas. They are, for example, they are actually syngases. Syngases can be contains hydrogen and CO, and they can be coupled under Fischer-Tropsch reaction to produce aviation fuels. The challenge is apparently is the catalyst. The catalyst will be contaminated. Sometimes it will defunctionalized. So that engineers are trying to figure out the ways to improve the process. So there is a great opportunity for US to export the SAF to the European Union, right? So as you can see, they have a very restricted, mandates for SAF implementation to I think even 70% of SAF by 2050, and the UK has similar, standards as well. As you can see, if you consider about right now, they are about 900 million gallons per year for 6% of by 2030, and their demand is continuously increasing. And most of the SAF now are produced using so-called HEFA SAF process. As I mentioned, the HEFA SAF is a hydroprocessed esterified fatty acids that's mostly supplied by those crop-based oils. But as you can see, many pathways I mentioned, you can produce the SAF, right? So the first one is oil to jet, which is I just mentioned is using the HEFA SAF process. You can use a Fischer-Tropsch process using syngas to produce jet fuel. Also, you can convert sugars to alcohol, including ethanol or butanol. Gevo is one of the companies that they actually produce this jet fuel using this technology. Now, LanzaJet is another company. They're commercializing ethanol to jet process. Sugar to fuel, jet fuel, for example, I think Virent is one of the companies. They do this aqueous phase reforming to convert the sugars to jet fuels. And you can produce many of the process can produce. For example, the HEFA SAF process produces this straight chain hydrocarbons, paraffins. But straight chain paraffins has a low performance at poor performance at low temperatures because of the viscosities. So sometimes you have to add those isoparaffins, and also aromatics and dicyclohexanes will help to improve this performance. So these technologies, many of the technology has been approved by the ASTM standards, right? So from different feedstocks, you can find different tailored technologies to convert that into SAF, and then you have a maximum ratio. So far, most of the standards are actually capped at 50% of the mixing ratio. And I just want to say, well, many of them are based on terrestrial biomass, crop oils, and waste materials. There are a total about 8 technologies right now. The last one is actually being approved. And there's another, I think, people are looking into for CO2, electrified CO2 to intermediates to produce SAF, and I think that will be also interesting. And some of the companies is trying to pass that standards as well. HEFA SAF, although is the biggest supply for commercial SAF, right? So you are converting those triglycerides or free fatty acids, try to remove the glycerol, and then you do the hydro processing, do hydro treating it, and you can do the hydro isomerization to produce all these straight chain or branched paraffins. But one of the challenges for HEFA SAF is it is directly competing with biodiesels. As you know, biodiesel in the United States have about 46 billion gallons per year of demand. And if we are actually using these soybeans or canola oil FOG, we are directly competing with the feedstock with them. I believe about 2 years ago, I see the price for this feedstock, especially for FOG, increased to almost $6 to $8 per gallon. So that actually limits the profit for this SAF production from FOG. So we have to find alternative ways. One of the technology I'm developing is using corn stover waste. So this technology is developed, is sponsored by the US DOE, and I developed at the National Renewable Energy Laboratory. We have worked with Conestoga, the Sapphire Renewables. We are building a 10 tons biomass per day to produce ethanol using this called deacylation mechanical refining process. So basically, what we do is we have the corn stover, we actually chop it in the plant, and then we add chemicals to remove some of the unwanted materials, and we have the cellulose and hemicellulose and hydrolyze it into sugars. Then we ferment it into ethanol, and ethanol further being oligomerized will be dehydrated, oligomerized, and finally hydrotreated to produce SAF. So this is work also collaborates with LanzaJet. So with that, I want to thank you for having me here today. It's my honor to be a presenter today. So thank you. Yeah.
Thank you, Xiaowen. It was great to hear your talk, and I learned a lot. Now I have a small amount of understanding when I see all those big SAF tanks at the major airports I land in, what's going on there. All right, well, next up we have Bob McCormick. Bob is a senior research fellow and platform leader for NLR, formerly NREL's fuel and combustion research. His work focuses on end-use issues and fuel engine interactions with alternative fuels, primarily biofuels, including ethanol, biodiesel, and bio-derived diesel and jet fuels. He has a PhD in chemical engineering and is a fellow of SAE International. And Bob does not have a presentation today, but hopefully he'll tell us a little bit more as a springboard for, and we better have time for questions afterwards so that he can answer some of those. Take it away, Bob. Thank you.
Thank you for the nice introduction. Yes, I was just hoping to answer questions today. And as was mentioned, our work for my team at NLR focuses on end-use.
Bob, I think you are cutting in and out, unfortunately. All right, Bob, I think we're still having problems hearing you. So why don't we go on to Tim for his presentation, and we'll hope to be able to fix some of your issues in the meantime and hold some time for question and answers with you. So pivoting to Tim Leach, I have been working with Tim for quite a few years now in the Alaska arena. He's the director of the Alaska Clean Cities and Communities Coalition. This has been a while in the making, but is a fairly new coalition. It's a partnership of organizations led by subject matter experts that exists to advance U.S. and Alaska leadership in the transportation sector. He'll talk a lot more about that. So I'll just skip on to say that he's also the deputy director of transportation for Launch Alaska, which is an Anchorage, Alaska-based nonprofit to catalyze rapid innovation to strengthen energy, transportation, and industrial systems. So he's been working in this arena for over 20 years. And like I said, it's been my pleasure to work with him on electric vehicles. And I know his work has encompassed so much more. So go ahead, Tim.
Thanks so much. So yeah, as Michelle just mentioned, I'm the coalition director for the Alaska Clean Cities and Communities Coalition here today, talking about our alternative fuel options, as well as give a little bit of background. Very briefly, the Department of Energy partnership that we have, the CCNC is the Clean Cities and Communities Coalition network across the United States there. You can see Alaska's currently in gray. That color of Alaska right now is gray, but next week should switch to blue as we become a formally designated coalition. The main purpose here, or the mission at the federal level, is really to promote energy security and prosperity, economic prosperity, improve air quality, and leverage domestic fuel sources. So alternative fuels are squarely within the bailiwick here. Over the 30 plus years, 33, I believe, there's been quite a large impact. I won't actually go over these points just to save us a little bit of time, but you can see there's been quite a lot of impact across alternative fuel adoption and vehicle adoption in the United States as a whole. And of course, we in Alaska are just getting started on our portion of the journey. Our mission for the Alaska Clean Cities and Communities Coalition is largely mirroring what I mentioned at the federal level with alternative fuel promotion and economic prosperity and energy security core to that mission. We do that in a few ways, very typical to the types of nonprofit work that you may be familiar with. We connect entities or fleet managers to tools. We build partnerships between those asset owners and the technology providers, whether they're from the startup world or from the legacy technology provider world, give them additional technical assistance, and of course, collaborate with them on funding. And this was, for Michelle and myself anyway, one of the reasons we actually started the Alaska Clean Cities and Communities Coalition was access to federal funds. In some cases, for some DOE money requires that you need a Clean Cities team or Clean Cities and Communities team on the ground. Now, very briefly, we've talked a fair bit about Alaska, but for folks who need a little bit more context, there was a mention of North Dakota yesterday in similar or comparison in terms of population. When it comes to transportation systems, there's really a vast difference that we have in Alaska. While we are similar in population to North Dakota, we have, about 1/10 of the road miles of the state of North Dakota and a much larger area, of course, of land area. The state of Alaska has a land area of about 1/5 of the land area of the lower 48, right? So lots of different types of transportation needed. Alternative fuels, we've talked a lot about them obviously in the last 2 days, but why should we care in Alaska? This is just a bullet point recap of what we've mostly heard already from previous speakers. Ted Stevens Anchorage International, of course, is a critical gas station for Trans-Pacific cargo. Just over 50% of the air cargo that moves between Asia and North America stops in Anchorage. Planes, of course, are capable of flying the distance between Asia and North America markets. It's more profitable for the companies to stop and refuel at Ted Stevens here in Anchorage. So there is a large fuel demand, as we heard, I believe, from Andrew Jensen, Mike McElhaney early, and of course reiterated by Deputy Commissioner Keith. I think it's about 800 to 900 million gallons of fuel used annually there. Port of Alaska, it's a U.S. commercial strategic seaport, and so we get a lot of the fuel needed for aviation, needed for ground aviation across the dock here. That aviation, as I believe Mike McElhaney mentioned, is not just for the civilian market. So there's a Department of Defense or Department of War application. The valve yard in this picture, or just near this picture anyway, also goes up the hill that's in the background to Joint Base Elmendorf-Richardson. So really, there are fuels that come across the dock that go up the hill. If we can look at that total demand, civilian and defense, there's a huge amount of fuel opportunity for switching, especially where it's economic, and provides some strategic advantage for reduced supply chain risk as well. Dutch Harbor, if we look at the maritime, this is one of the maritime applications that we've heard a little bit about. It's the largest commercial seaport by volume in the U.S. And of course, it's also right along, about halfway along the Great Circle route for at least parts of the season for maritime shipping between the Asian and North American markets. Other maritime applications we heard a little bit about from Greg Dolan on the methanol conversation in regards to the green shipping corridor. Of course, we have cruise ships. We don't just talk about the freight here that's moving in our waters or to our markets. Across our modalities of transportation, we are seeing and hearing that there is demand for alternative fuels. We already heard that from Deputy Commissioner Keith quite in detail about the aviation demand, 150 million gallons per year, basically in letters of interest. There on the smaller aviation side, we'll touch on the technology options in a second. There's an interest in reducing cost, especially for our regional and sub-regional transport by air. Maritime, we've already heard quite a bit about that, but both on small vessels, if we're thinking about water taxis, larger vessels, if we're talking about fishing vessels, you can see an example there in the photo. In particular, some of the processors out in the Aleutian Islands we've been working with, and already, of course, we've touched on the container ships and the ro-ro vessels, like we just heard from Kelly Scott. Ground vehicles, similarly, there's an interest in reducing cost and improving service and function, and if possible, also reducing emissions. I think one of the things that's unique about Alaska here, though, across all of these options is that we have that huge land area that we talked about, and we have an immense amount of technical capability for renewable resource development, as well as some of the biomass that we heard Deputy Commissioner Keith talk about. And those can be key or are really key ingredients for the production of alternative fuels. All of this is to say there's this tremendous economic development opportunity as we look at ways to improve our energy security and reduce the risk of price volatility that we heard Andrew Jensen and Mike McElhaney talk about at the very head of the discussion yesterday. Very quickly, we'll look at some of the current alternative fuel vehicle snapshots and some opportunities. The graph on the right, no need to pay too much attention to that. That's electric vehicles. We're not focusing on that today, but I would say with this, that's been the dominant alternative fuel vehicle type that we've seen in Alaska. The bullets on the left here give you a little bit more detail about what those types of EVs are. And you can also see in the latter bullet points, really we have very few, currently we have very few other fueled vehicles, some CNG, primarily a few on the North Slope, and then there's going to be an increasing number for Fairbanks as they move their transit fleet over to CNG there. And then, of course, we just heard from Kelly about the LNG that Tote's been working in their two vessels. From a market attribution or our attribution methodology perspective, we can't claim their fuel because they bunker the LNG fuel for Totamine because they're refueled down in the Washington market. But we might be able to change that, right? That's the whole point of the conversation. We've already talked at length about SAF, so I won't touch on this much more other than to say, there's strong opportunity and interest here because this is the largest out of, our fuel types. This is the largest driver of energy consumption emissions that we have in the state. I will mention a couple other options for aviation that are especially useful at this point if we're talking about regional and sub-regional travel, shorter distances. Hybrid electric aircraft, one company, Ampere, that we've worked with, has done some impressive work in this space, including one of the transits that they made from the Southern California area up to Fairbanks a few years back. Cost savings, just like a hybrid electric vehicle, the Priuses of current day, there are emissions benefits as well as operational cost savings there. They're working on retrofits, similar to Kelly Totes mentioned, the retrofit market in any sector, housing, buildings, transportation, that's a market we really need to address. Ampere's got some options for that. They're also working on clean sheet designs for larger aircraft. Hydrogen fuel cell aircraft, this is, as far as our timeline, probably further out to the right on that timeline. But Zero Avia is another company we've been working with that has potential to meet the service mission for various types of aircraft. Those regional ones, you can see that's a Dornier in the picture. That's actually testing a power plant, 600 kilowatt power plant, fuel cell power plant that would be dropped into a Cessna Caravan, which is really a workhorse aircraft for us here in Alaska. They've also got designs for a 2 megawatt power plant that would be more appropriate for regional jets and other larger turboprops. And eventually they've got that clean sheet design up to the narrow body, and they're talking about wide body as well. So eventually we'll get there. As you look at the options for aviation, SAF is going to be the primary drop-in, but eventually we need to get towards these as well. Contrails, I'll mention that word. If anybody's interested, we can talk about it later. Okay, renewable diesel. We did hear some that this is really the behind CNG. Renewable diesel is the most in-demand fuel in the United States, alternative fuel in the United States. And we don't have any fuel yet up here, but the fuel providers are ready. Delta Western and Crowley, for example, are ready to deliver it. Ideally, of course, as we've been talking about, we'd love to produce that here, and there's an option at least that's being considered by DOT with that biorefinery with renewable diesel as one output. Hydrogen fuel cells. This is a consideration that some, in particular, will be working with the Port of Alaska to look at alternatives for yard tractors. That's a yard tractor in the photo. To see if hydrogen fuel cells make sense as compared to battery electric or renewable diesel, renewable natural gas, things like that. And then almost last slide here. We are, of course, very aware that there are options, as we've already been discussing, for battery electric, hybrid electric, and alternative fuels for various marine vessels. These have already been discussed at length, but there are, of course, many good examples that we've seen in person over in Scandinavia and then also down in San Francisco. Thanks very much. I'll leave it there.
Thank you very much, Tim. And I think we have Bob back with us. So, Bob, if you could go ahead and say the remarks that you were going to say, and then we'll lob some questions at you.
Sounds good. Michelle, I'm going to leave my video off in case it was a bandwidth issue. I just wanted to say that my team has primarily worked on liquid fuels, alternative fuels, biofuels, really with a pretty near-term focus, nearer term than hydrogen and ammonia, for example. We've done extensive work on ethanol, biodiesel, renewable diesel, fuels for on and off highway applications, including marine shipping. So I could talk to the use of methanol and ethanol in shipping. Our recent research is focused almost entirely on synthetic and sustainable aviation fuels. And we're very familiar with the ASTM standards and processes for gasoline, diesel, and jet fuels. And so if you have any questions on any of that, please toss them my way.
Well, I can ask a first question. So ethanol has, I believe, been discussed in a previous section, but hasn't been brought up much in this section, but is a widespread alternative fuel, if you will, that's been in use in vehicles for a long time, blended. Can you speak a little bit to the Alaska factor around some of the supply chain availability, maybe local production, as well as cold weather and other issues that come up with some of these alternative fuels? So the Alaska context for, you can touch on ethanol, but certainly some of these other fuels that have been mentioned, are there things we need to keep in mind given our cold climate and some of the other supply chain and restrictions around, not having large agricultural industry for byproducts or growing some of the feedstocks?
That's a great question. Ethanol has been used in cars since there were cars, since the Model T. And today in the U.S., at least 95% of the gasoline contains ethanol, maybe more like 98%. In terms of operation in cold weather, I can't think of any reason why ethanol would be a problem in really cold weather. So I think the reason why maybe it's not used in Alaska is just logistics, in that it's not produced in Alaska. Would have to be brought in on tankers. The benefits of using ethanol are that blending ethanol does reduce the price of gasoline a few cents a gallon, because it's cheaper than gasoline, and it allows the petroleum refiners to use ethanol to meet the octane number requirement of gasoline, and they can make a less expensive hydrocarbon portion of the gasoline. Potentially, you could produce ethanol in Alaska from biomass resources, not necessarily agricultural resources, but forestry resources, although that's not really being done anywhere yet. That's sort of a next generation ethanol production process. There was more.
Well, what about these same considerations around some of the other biofuels that are being discussed or have been discussed in this panel? Do any of them have cold weather concerns? Are there any that would be easier for us supply chain wise or local manufacturer to move into the Alaska market?
I think the one that would have obvious cold weather concerns would be biodiesel. We talk about diesel fuels for wintertime use in terms of their cloud point, which is the temperature where things start to crystallize out of the fuel. And for the best form of biodiesel for cold weather, things are going to start to come out at 32F. And for 100% biodiesel. Now you could potentially blend it at very low levels in a wintertime diesel fuel, but it just may not be the best choice for Alaska. From the same feedstocks, which are fats, oils, and greases, you can make renewable diesel. It can be made with any cloud point you want. In an almost identical process, you turn fats, oil, and greases into jet fuel, which has a freezing point below -40 C. So I would think the cold wintertime diesel fuels in Alaska probably look a lot like jet fuel. For other like gaseous fuels, I don't really see any cold weather constraints on natural gas, hydrogen. Yeah, I think those would, you could potentially have some issue, but it's not a showstopper. It's something that could be dealt with.
Awesome. Thanks, Bob. Well, Mari, who is not exactly the listening public as our moderator for the whole workshop, has put a question in the chat for you, Xiaowen. We've heard from Deputy Commissioner Keith that the facility they are considering may be able to co-produce SAF, RD, and naphtha, renewable diesel, and naphtha. Do you have an explanation for how this would work, that we would co-produce all those fuels?
Sure. Yeah. So when you have a lipid source like oil comes into a facility and you want to produce the SAF, what you do is mainly you actually do you want to remove the oxygen, you want to saturate the lipid, but based on the process, you will produce different carbon numbers of hydrocarbons, right? And you want to distill it and to separate those to make into different products. For example, the lighter part, based on different boiling temperature, you can separate that into light part, which is like a naphtha and renewable naphtha. The middle point is a jet fuel, right? So jet fuel has a carbon C9 to C12, C13, and the heavy part is renewable diesel. So that is trying to utilize all the products that we produce from the lipid oil. So that is main. So that's usually it's happening in a refinery, right? So you can produce multiple products and maximize your profit and feedstock usage from this refinery plant. So I hope that answers your question. Yeah.
I believe so. Yeah, it answers it for me. Thank you very much. So yes. I guess we're getting pretty near the end of our time for this session. I'm going to ask a question I have. We are seeing uptake of light-duty electric vehicles on the roads here in Alaska, and that definitely kind of seems to be the winning alternative right now, at least for light-duty vehicles. I've certainly heard of some natural gas buses been tried or on the road. So there's some limited examples, and there's the Tote Marine LNG ships. What do you think in the near term? What are the next biggest opportunities for renewable fuels or alternative fuels in the Alaska market? All of you maybe have some view from your piece of research or knowing how these things are going. And is that maybe in the aviation sector, in the marine sector, in ground transportation, maybe in the heavy duty vehicles? Where are we going to see some movement next? Tim, maybe you could start us off.
Sure. Yeah, I think from an economic development or opportunity size perspective, the aviation sector, has the largest fuel demand there. So whether you're coming at it from dollars spent and how can we reduce those dollars, or from the emissions side, that's the biggest piece of the pie, or a separate pie entirely. And then there are orders of magnitude smaller amounts of fuel used for marine that's fueled up here in Alaska. I should mention that, and then ground. So I think the biggest opportunity there is really the refueling of jets out of Ted Stevens Anchorage International and secondarily up in Fairbanks. So getting the fuel production, but also the distribution up to alternative locations is going to be really critical for that. If there was one thing I had to put my dollars into, that would probably be the place.
Rookie mistake, muted. From our other panelists, any outside perspective or maybe what you expect to see in the US as a whole moving forward in the next few years with some of these alternative fuels?
Well, if I can go next, I'd say that where things seem to be moving the quickest to me is in marine shipping. Not just LNG, but the move to methanol and ethanol dual fuel ships seems to have a lot more momentum even than sustainable aviation fuel. And I do think sustainable aviation fuel has a lot of momentum. It's just a lot harder problem and going to be a little slower to develop. And, we're working very hard to try to figure out how it could go faster. But, a lot of it has to do with a expensive and slow fuel approval process, which makes sense for airplanes.
And Xiaowen, you get closing comments if you have anything you'd like to add to that discussion.
I would say, producing renewable fuels from renewable resources will, one of the key challenge for to me is that the cost, right? So if we want to apply this to society, we also not only have to think about the carbon credits or carbon intensity, but also we have to think about all the costs for producing these. And if we want to move forward to use to apply this into our every sectors, I think developing value-added products along with SAF or along with those renewable energies are very important. So we want to do a full utilization of the renewable feedstocks and apply that to the fuel sectors. I think is a key to make a success of the renewable energy.
Thank you. I appreciate the great presentations and the input of all the panelists. I learned a lot, at least. Thank you very much.
Thank you.
Thank you.
Thank you, Michelle and Tim and Bob and Xiaowen. You guys are our last presenters, so this actually concludes our second day of this workshop. I want to thank so much all the participants, speakers, moderators, attendees. Thank you all for attending. And I understand that a lot of times these are, many people watch these afterwards. So thank you, future viewers who happen to have made it through the entire workshop. And thank you, huge thanks to Sarah and Caroline and the event support team who make this as painless as possible for people who don't like to get in front of other people and talk. So thanks so much for everything. Please, we hope to see you all at the Alaska Sustainable Energy Conference at the Denina Center in Anchorage, May 19th through 21. You can register at the link that Sarah Caroline will post there, www.alaskasustainableenergy.com. We are going to be sending a short survey following this workshop, and we'd love to hear about your experience, how you think we could do better, what we did good. That will help us improve future workshops. You can access the survey by scanning the QR code on the screen now. I'm totally messing up the order that they were going to put these slides in. Sorry, but they're working with it. So I think that's it. Recordings will be available at the website that will also be posted here in the chat very soon, out of order. That's it. Thank you, everybody.